First speaker here, Parker Ziegler. He's at Berkeley and co-authors at Berkeley as well. And Parker's going to talk to us about fast direct manipulation programming with patch reconciliation correspondence. Thank you, Parker.
All right, thanks so much. All right, so good morning, folks. My name is Parker Ziegler. I'm a recently minted PhD candidate at the University of California, Berkeley. And my research focuses on bridging the gaps between graphical user interfaces and programming languages to build new kinds of interactive systems for working with data. And this paper, which is joint work with my collaborator Justin Lubin and my advisor Sarah Chasins, is one critical step towards that broader research vision. So the original motivation for this paper stems from this years-long journey I've been on to build a practical direct manipulation programming system for developing interactive maps, which are these very rich graphics that are increasingly essential to data reporting in today's newsrooms. So let me show you what I mean by a direct manipulation programming system. So these are programming environments that allow users to edit not only the program, but also the output produced by that program using these familiar interactions from direct manipulation interfaces. And then simultaneously, the system is responsible for synthesizing some kind of program transformation to capture those output modifications. So what you're seeing here is the actual system that we built called CartoKit, where I'm in here manipulating this output map, and the system is modifying the corresponding JavaScript program in real time. And I got really excited about these kinds of tools after doing some observational research with data journalists, climate scientists, social scientists, all of whom work with geospatial data. And from observing these domain experts, I found that many rely very heavily on direct manipulation interfaces for their exploratory data analysis and visualization, but eventually almost always need access to a program to support future customization or replication of their work. And so ever since, I've been really excited about how do we unify these two into a single interactive system. Now, our primary challenge in building a direct manipulation programming system is figuring out how to synchronize the program with the output at interactive speeds. And prior systems have tended to use an approach that looks something kind of like the following. So we have some kind of GUI interaction that a user is taking to trigger this output update. That also is triggering some program update process that is handled by this procedure that we like to call patch. Patch is responsible for synthesizing and applying that program transformation. And then finally, we reevaluate the full program to produce the updated output. And we like to call this the patch eval architecture because we have these sequentially executing patch and forward evaluation steps. In general, this architecture has worked very, very well in settings where just reevaluating the program on every GUI interaction is sufficiently fast. So things like vector graphics and web pages. But when we thought about using this architecture to build CartoKit, we quickly found that it wasn't actually going to be tractable. So why is that? Well, in our context, it's pretty common to have computation over tens of thousands to millions of records. We're often running these very expensive geospatial data transformation algorithms in a resource-constrained environment like a web browser. And then we have a very heavy graphics workload in WebGL. So to give just one example, here's a reproduction of a map published in the Washington Post. The JavaScript program that produces this map takes 18 seconds to evaluate and actually fully render the pixels to the screen. And in this case, it actually makes some sense why we're computing over nearly 500,000 rows and about 1/4 of a gigabyte of data, all of which has to be parsed and stored in memory. So in general, forward evaluation in this context is just going to be way too slow for an interactive system. So seeing this problem, I think naturally we might think, OK, big data, long-running programs, maybe caching could sort of help in some way. And on the surface, I think it sounds like a plausible idea, but think for just a second about what adding caching to this diagram would sort of concretely entail. So we would need some sort of cache-aware custom evaluator that could analyze the expression in the program under evaluation and determine that some prior results from the cache could be reused for a given subcomputation. And then we need some logic in our application for actually building, maintaining, and invalidating that cache based on the interactions that the user is taking in the GUI. And that is sort of notoriously difficult to get right. So again, it's not impossible to get these things right. It's just very, very hard. And if we do mess up, so let's say we do something like erroneously reuse some cached result when we shouldn't, we can get into this really nasty state where the correspondence between our program and output are actually broken. And so from here on out, every GUI interaction that we're taking in this system is seeing an inconsistent state of the program and output. And that's kind of breaking the core obligation. So in this paper, we were really focused on trying to think about, is there something simpler? How can we actually guarantee this program output synchrony without relying on full program reevaluation every single time? All right, so one observation we can make if we look at this diagram is that we're actually already applying these very small syntactic transformations to the program via this patch operation. So could we pair this with some other operation that's responsible for making semantic transformations on the output? Now, if we've taken care of updating the output directly, can we actually just cut forward evaluation out of this loop entirely? And more or less, that's sort of the key trick behind the work. So that leads me to sort of the core technical contribution here, which is the idea of our patch reconciliation architecture backed by this formal notion of patch reconciliation correspondence. So let's dive into the details of how this works. So again, we'll start with some kind of GUI interaction, but this time this dispatches this data structure that we call a diff, which really just encodes sort of the key information about the output modification the user is making. And now, in addition to our usual patch component, we have this separate reconciliation or recon function. And so we've seen patch before. Patch handles updating the program, and recon now is responsible for directly modifying the output based on that diff. So the key thing to notice here is there's actually no arrow between the program and the output. We're never reevaluating the program in this process. And so, doing that, making that process sound, relies on there being some sort of correspondence between these patch and recon functions. That in essence, the program transformation applied by patch is sort of effectively emulated by the change that recon is applying to the output. And we're going to dive in a little bit into sort of formally how we define that and how we prove that sound. But to just take one quick step back, think about how this actually changes what a system developer is doing here. It really sort of focuses their attention on thinking about, for some given program update triggered by this GUI interaction, how do I minimally update the output to bring the two into sync? And what's really nice about this framing is that we can take a lot of inspiration from two areas of the literature that haven't really been connected before. So on the left here, there's all the great work in direct manipulation programming on how to implement patch for different kinds of languages and increasingly complex GUI interactions. And then on the right, we can actually take a lot of inspiration from the incremental evaluation literature to think about how do we make this sort of small change to the output based on sort of a minimal program update. All right, so to return to sort of that core problem, the key insight of this work is really, let's pair the syntactic operation that we have for updating the program, this patch operation, with a semantic operation for directly updating the output, which is reconciliation. Okay, so I mentioned that these two things need to share some kind of correspondence, so let's dive into formally what we mean there. All right, so consider some language L consisting of the following elements. We have a set of programs, a set of output values, a semantics that evaluates programs to outputs, a set of diffs, and then this syntactic diffing operation patch, which takes in a diff in the current program and produces the updated program as output. So our goal then is to define a reconciliation function, which is a function that takes in a diff in the current output and produces some modified output, such that for all diffs, the following equality holds. And we can represent this equality visually as this commutative diagram here. All right, so let's kind of break this down step by step. On the left here, we're saying that if we first start by patching a program based on that diff to a new program P prime, and then we evaluate that to a new output V prime, that should be identical to first evaluating the program to the output and then reconciling that output based on the diff. And if showing this equality is what's going to allow us to rely on these parallel applications of patch and recon to reach P prime and V prime respectively without actually needing to run this eval step. So we actually instantiated this full framework in CartoKit, defining a notion of programs, output values, our semantics, our set of diffs, and then our implementations of the patch and recon functions. There's a lot of Greek up on this slide, so I think this is actually best understood through a concrete example. So here's a map that a user could make in CartoKit. This map consists of 3 layers, one for US counties, one for US urban areas, and one that shows the perimeters of wildland fires in the US over the past year. In CartoKit, we model this program as essentially a dictionary of layer definitions, which map a layer ID to these triples consisting of a layer type, like polygon, proportional symbol, dot density, their associated geospatial vector data, and then these style objects, which represent the visual encoding of the data on the map. And then through repeated application of our eval layer rule, we'll transform these layer definitions into actual graphical marks that are rendered on the screen. And then the union of just all of those marks is what we consider sort of our output value here, our map. All right, so now let's say that a user is going to take one of these GUI interactions. They're going to actually transform this wildfires layer to what's called a proportional symbol layer. And this transformation is going to allow them to sort of compare the relative severity of these fires in sort of a much more direct way than a pure polygon layer. So that interaction in our system dispatches this diff, the transform layer diff, that applies to this wildfires layer and includes this transform function that we'll talk about in a second. So let's see how patch is going to operate over this diff. So here's our inference rule for patch for the transform layer diff, and it can be read as follows. We'll first start by looking up the layer in the program by ID, and then we'll actually apply this transform function to produce a new layer definition, in this case for a proportional symbol layer with some modified data and a modified visual encoding. And then in the conclusion, we're just substituting that new layer definition back into the program. And so we end up with a sort of updated program on the other side. All right, so now let's see how recon is sort of operating here. All right, so here's our inference rule for recon, which we can kind of read as follows. We'll first start by creating this set, m prime, by actually mapping that transform function over all marks in the wildfires layer. So concretely, this can actually be implemented in our system as an in-place update of existing marks. And then this set, m double prime, is actually just all other existing marks that are not impacted by this diff, so the marks from the two other layers. So these can actually just be reused. They already exist in our output. And then the conclusion of reconciliation is just the union of those sets of marks. And so again, we end up with this new output value, this union of these graphical marks, the first which can be generated through an in-place update, and the latter two are just reused from the prior output. And then the proof here really just involves saying that, hey, if we had evaluated that patch-modified program we saw earlier, it would produce exactly the same set of graphical marks that were produced in our reconciliation process. So if you're interested to see all of the proof cases, they're available in the supplementary appendix of the paper. All right, so let's dive into how we actually evaluated this system. We were really curious to understand patch recon's impact on interface latency, right? How much faster does a direct manipulation programming system feel from a user's perspective in this case? So to do this, we actually re-implemented 6 maps published by national newsrooms using both our patch recon architecture and the patch eval architecture. And then for every GUI interaction required to develop these maps, we measured how much time does it take between triggering that GUI interaction and seeing the program and output sort of fully update on screen and become visible to the user. And across all 80 cases, we found that the patch reconciliation architecture led to faster updates, and the median speedup was about a 3x. We saw a 3x reduction in UI latency. In addition, there's this really nice result where we saw that longer running programs actually saw larger speedups. So we actually get more benefit from patch recon in cases where patch eval sort of takes longer and longer to run. So up here in the upper right, we actually saw a 6x speedup on a program that originally took 18 seconds to evaluate under patch eval. Okay, great. So we've seen that this seems to work really nicely for our domain and language, but what controls whether we can apply this elsewhere? And there's sort of one key insight to note here, which is to look at the signature of that recon function, right? Recon takes in diffs and values and produces an updated value. So the complexity of implementing recon is actually contingent on the user actions that a system developer makes available, the things that actually generate these diffs. But it's not actually tied at all to the underlying language. So to see that a little bit more concretely, we can think about how we might implement patch recon for a system like Sketch and Sketch, which is a direct manipulation programming system for vector graphics. So Sketch and Sketch uses an Elm-like general purpose functional language, kind of shown here on the left, and evaluates that program to produce the SVG output here. So we can imagine that a user might do something like take this GUI interaction to change the color of this circle here. And the novelty of prior work in things like Sketch and Sketch was actually figuring out how do we do that patch operation in that context, which in this case actually involves updating that let binding for color to red. But interestingly, reconciliation can actually be pretty easy here. We just need to get references to these DOM nodes and then just call set attribute to actually set their fill to red. Now, a very astute reader will notice that this does rely on sort of tagging output values with some sort of shared identifier to know that a modification to this circle here is going to impact these others. But Sketch and Sketch actually already showed how to do that with this idea of provenance tracing, and in CartoKit we do it through the use of these layer IDs. All right, so to wrap up, I want to zoom back out and think a little bit about what's different now that patch recon is sort of in the mix. How does this change how we think about building these kinds of systems? And I think the one takeaway is that we can now actually think about applying direct manipulation programming to settings that were previously just way beyond its reach. So whether that's image processing, computer-aided design, animation and 3D modeling, any other context where we have long-running programs, data-intensive tasks, I'm really excited about how we can turn these kinds of rich interactive GUIs into sort of full-fledged programming environments. So that's it. We've presented kind of the key idea of our work in patch reconciliation correspondence and this patch recon architecture for developing direct manipulation programming systems that can scale to long-running programs. And then we actually use this to develop what we think is a very practical programming system for domain experts. So you can try out the system today at alpha.cartokit.dev. It is currently used by folks from a few national newsrooms in the United States. And if you're curious, check out the code or get in touch with me by email or Blue Sky. Thanks so much.
Thank you, Parker, for a great talk. We've got time for a few questions. I think we've got one at the front here.
Hello, Bhargav Kulkarni from the University of Utah. Thank you for the amazing talk. I was wondering, my question was how easy is it to create recon functions for something other than maps? And you kind of answered that with the Sketch and Sketch example. But I was wondering how easy was it to create the recon function? Or could I, given a patch, program, and values, can I synthesize a recon function like to use?
Great questions. I think a key thing to kind of understand about the recon function is it's more or less how application developers build UI today. It's actually not very different from how you would actually sort of build the UI. The challenge usually is that in this context, we actually have this program that we need to sort of keep updated. So implementing recon is not difficult, but kind of thinking about actually the diffs that you want to encode into your system, and both ensuring that there's kind of these corresponding patch and recon operations that can work over the diff, and this sort of proof of correspondence is sort of where the main challenge is. But recon itself is actually something that we suspect system developers just kind of already do very naturally. So yeah, I'm really excited about that sort of element of the system. Oh, I think
you have another question? Oh, we have one down here.
Oh, yeah.
It was my understanding, or correct me if I'm wrong, a diff corresponds directly to an action a user would take in a GUI. Is that correct?
Yes, so the actions that a user takes, dispatch diffs. Diffs are user defined by the system developer, so we had our particular subset of diffs that we defined in CartoKit, but they are something that are user defined, and then patch and recon are effectively sort of giving semantics to diffs. Like recon actually sort of gives semantics, and patching is sort of a pure syntactic update based on the diff.
Gotcha.
Yeah.
Okay, thanks.
Last question.
Thank you for the great talk. I was wondering if there is some kind of difficulty in the system depending on the interaction of the GUI. So are some interaction more difficult for the system to reconcile and then some are easier?
Yes, definitely. So any recon action in our system that is doing any sort of geospatial transformation has kind of this challenge of both performance overhead, but also we're updating both sort of data and stylistic encodings. And certain stylistic encodings are only valid for certain kinds of geospatial data. So those are much more tricky to reason about than sort of more simple operations that you would see in Figma or Illustrator around things like colors, opacity, stroke widths, those sort of more standard things. So yeah, there's definitely sort of a difference, and a system developer kind of needs to think about like, okay, what do they sort of want to take on in terms of the complexity? Yeah.
Thank you.
All right.
Fantastic. Let's thank Parker for a great talk. All right, our next speaker is Gavin Gray from Brown, and he's going to talk to us about an interactive debugger for Rust trait errors. Thank you, Gavin.
Thank you, Steve. So yes, today we will be talking about debugging trait errors in Rust. And I'm sure that many of you are not Rust developers, so I want to give you a sense of what it's like to be one. It's not important that you understand this code. What it is the simplest game possible made using Bevy, which is a game engine library for Rust. And there's a lot going on under the hood of this seemingly simple client code. If we look at the type signature for the add systems function, we see that the second parameter is required to implement into schedule configs, which is a trait. And for those of you who use the one true programming language, you would call this a type class. But today we're going to call them traits, so indulge me for a little bit. And we say that the parameter is bounded by the trait into schedule configs. Now, library authors are clever, and they use traits to check that parameters satisfy a specification. And I'm going to depict the problem with pictures so we don't have to look at any more really verbose Rust code. For a trait bound to type check, the compiler searches for a trait implementation proof. The tree in the background is what that search tree looks like, and the green path in the tree is the proof that this type has an implementation for the trait. I'll explain briefly the structure of this search tree. At the root, we have a trait bound, and beneath trait bounds are impl blocks. Again, for the Haskellites, those are class instances. And trait bounds and impl blocks are connected with dotted lines because they form an OR relationship. Only one impl block must be satisfied for the trait bound to be satisfied. Impl blocks may have themselves additional trait bounds, and these nodes are connected by solid lines because they form an AND relationship. That is, all children of an impl block must be satisfied for the impl block to be satisfied. This code does type check, but there's a common mistake that Bevy users make. They forget to write this type in their system parameters. This still looks like innocent code, however, the code no longer type checks. The search tree for this incorrect program does not find a proof. With this tree, it's not clear which one of those red X's is to blame for the error. Is it one of them, the one on the left, the one on the right? Is it both of them? And the problem gets even harder when I tell you that that's not the full search tree, this is the full search tree, and it has over 26,000 nodes. So that's a big problem. But a bigger problem for the user is that the trait inference process is a black box. Worse still is that the traits and impl blocks in this tree are all coming from the Bevy library. So you can't see them in your client code. The only information you get as the developer is that the type of your setup function does not implement the trait into schedule configs. To help us understand the problem at hand, let's walk through how the Rust compiler turns this proof search into a diagnostic. So with hundreds of failing obligations in the tree, which one should the compiler report? Well, the Rust compiler will take the least common ancestor of all these failures, which of course in this case is just the original trait bound, and it reports that as the root cause. The compiler reports where the error originated, including the line of code it came from, but furthermore, the compiler will add suggestions for types that do implement into schedule configs, which is these three circles in the tree. And this diagnostic is not all that helpful. And what I mean is that it doesn't facilitate localizing the actual error. The diagnostic only captures the top of the tree. All of the actual failing trait bounds, the nodes with the red X's, are below this circled region, and the compiler just threw them out. If the developer wants that information, they have to mentally recreate the proof search using documentation or source code. Now, we could do a handful of things to improve this diagnostic, and the Rust community is aware of this problem, so I want to tell you about the approach that they are taking. The Rust Foundation sponsored a community project to improve errors for trait-heavy crates. They looked at problems that real Rust developers had, they solicited for programs that exhibit bad error messages on Reddit, and the solution they landed on was this. Rust recently added a feature, similar to the Helium subset of Haskell, that allows library authors to annotate traits with domain-specific compiler messages. The main change to the diagnostic we built earlier is that the principal message now uses natural language. This is a domain-specific solution that requires action from library authors. So if the library you want to use doesn't have these annotations, well, you're out of luck and you're stuck with the generic messages. And these annotations do solve a problem, but not our problem. Our problem is that the information presented doesn't explain why setup isn't a valid system configuration. And explaining this why not question requires a non-trivial amount of context that isn't included in the diagnostic. For decades, we have relied on static textual diagnostics to communicate errors to developers. For simple programs with simple types, like this Fortran code from the 60s, this works great. But modern programming languages are not simple, and understanding an error may require more information than we would want to put in a textual diagnostic. Providing an interactive interface for an error allows us to include additional context without overwhelming the developer. What I am not advocating for is just using a GUI. People have tried to slap GUIs on similar problems in the past, and developers did the same, or sometimes they did even worse. So we can't just use a GUI. We need to be careful about how we design the interface and make sure that it's task-driven and well-crafted for the specific task. So now we'll get into the details of Argus, which is our interactive debugger for Rust trait errors. We'll talk about its design and how it fixes the limitations I've mentioned so far. The default interface shown is what we call the bottom-up interface. That means you are seeing the leaf nodes with the unsatisfied trait bounds. The bound currently shown in the interface on the left represents the pink highlighted node in the tree, and I'll mark it with that pink dot for us to remember what it is. Now, as I said before, there isn't just one failing leaf node, but there's a few hundred that are hidden behind this toggle. Each of these unsatisfied trait bounds represents one way to fix the program. If you take any one of these obligations and change the program such that the bound is now satisfied, a proof will be found. The developer has an intended program semantic in mind, and our problem is that we want to find a trait bound in this list that, when fixed, produces a program that matches their intent. The only thing we know about the user's intent is the program and the types they wrote. So our working assumption is that fewer changes to the code is probably better. And we developed a heuristic called inertia that estimates how intrusive the program change would be in order to satisfy a failing trait bound. And then we sort the full list of failing obligations by their inertia. As an example, consider the second bound in this list. If we wanted to satisfy this trait bound, then setup would need to be a function with 2 parameters instead of 1. The first is a mutable reference to the world, whatever that is, and the second one is an uninstantiated type variable that, when instantiated, better implements system param. Now, fixing that obligation is a lot of work, much more work than making the parameter to the function we already have with the correct arity implement system param. And even though we sort this list by inertia, it may not be obvious to the user which one they want to fix. Recall that the traits and implementation blocks in this tree are sort of implementation details of the Bevy library, not necessarily something the user is supposed to know about. So they might need additional context. And the context they would want is the provenance of the failing obligation. In other words, why does this bound need to be satisfied? As a reminder, in the interface, we're looking at the pink node in the tree, and as users incrementally unfold the tree, they traverse the tree from bottom upward. At the bottom of the interface, we're looking at the blue node in the tree, and by expanding the bottom-up interface, the user has the path from the pink node to the blue node, which represents the full provenance of this trait bound. Even further context is available if the user control-clicks on any symbol in the interface. We use the IDE jump to definition functionality to open up the source code for a type, trait, or implementation block. The bottom-up view facilitates localizing the root cause of a trait error, but it shows only the failing trait bounds. And sometimes the user may want the entire tree, including bounds that did succeed for maximal context. So we also provide the top-down interface, which is simply a window into the full search tree. The trait bound you see on the left is now the blue node in the tree, and as users explore the tree downward, they incrementally expand the children of each node. Here we see the 3 impl blocks for into schedule configs. And with enough exploration, the user can locate the unsatisfied bound at the leaf that we inspected in the bottom-up view. There's a lot of contextual information in the search tree, and we don't want to overwhelm the user with too much at once. This is why we decided to use incremental unfolding in the UI, but we also elide information by default. For example, where clauses and implementation blocks, type parameters, and some miscellaneous types like that of our setup function. All of these toggle on click when the user wishes to see the full information. The bottom-up and top-down interfaces provide complementary views of the information, and each has its own strengths and use cases. The big question still remains: does it actually help developers localize their trait errors, or did we make a cute interface with some nice icons? Well, of course, we ran a user study to find out. We recruited 25 participants of varied experience. For each task, we gave them a small program which was randomly selected from our pool of 7 tasks. 3 of these task programs use real-world libraries: Axum, a web framework; Bevy, the game engine we've seen today; and Diesel, a SQL query builder. 4 of the programs use synthetic libraries that we created just for this study. The Brew Crate provides a DSL for brewing potions, and the Space Crate provides a DSL for constructing intergalactic flight plans across some made-up universe. The synthetic crates allow us to test participants in domains we know are unfamiliar. But in order for the synthetic and the real-world tasks to be comparable, we designed the library such that the trait inference trees between the real-world and synthetic libraries are equivalent. Participants were instructed that the task program was from their coworker and that they should explain to their coworker why the program didn't compile, and to provide a semantic preserving program fix that results in type-correct code. Participants had a maximum of 10 minutes per task, and we distinguish between time spent localizing an error and time spent fixing an error because our hypothesis is that Argus is more helpful in the localization process. With our running example program, a proper localization would be pointing out specifically the issue with the function parameter. For example, a successful localization from a participant came when they said, the parameters for setup are incorrect, mesh assets doesn't implement system param. Fixing this error would require participants to wrap the parameter in the resmute type we saw previously. We believe that Argus is less helpful in fixing errors because it requires knowledge of the library API, like the existence of the resmute type. And some of these real-world APIs are quite large. This is also difficult because resmute doesn't occur in the trait inference tree. Argus plays a few tricks to help people find these types, but it's not the tool's main focus. Participants engaged in 4 debugging tasks. They could use any tools, including LLMs and Google. In 2 of the tasks, they could additionally use Argus, and using Argus first or second was randomized. So how did our 25 participants do? This plot shows the localization rate, higher is better. The blue bar is participants who don't have Argus, and the yellow bar is participants who do have Argus. We observed that participants did significantly better when they had access to Argus. The next plot shows the time spent localizing an error. Here, lower is better. And again, we observe that participants localized significantly faster with Argus. And it's important that I point out the scary red line at the top of this plot. As a reminder, participants were cut off at 10 minutes. So for localization time without Argus, this really shows a lower bound. We don't know how long these participants would have taken if they had all day. As we hypothesized, participants localized significantly more errors and faster with Argus. Now let's look at how they did fixing their programs. For the fix rate, higher is better, and participants fixed a few more errors with Argus than without. And for the fix time, again, lower is better. Participants fixed programs a bit faster with Argus. Once again, note that 10-minute ceiling. So Argus significantly improved localization rate and time and help developers fix their code. And this is great for the Rust community. But there are a lot of us who don't use Rust every day. But there are also a lot of search-based PL mechanisms in the world. Today, I talked about type class resolution, but there's also SMT-based tools, and there's even dynamic things like multi-method dispatch. I claim that all of these communities and more could benefit from an Argus-like interface. So if you work on a language with complex types or an involved runtime mechanism, you need an Argus-like panel. And fortunately, I've seen all your talks, so I know that there's plenty of you working in this area. I've gone through a lot today, so I'm happy to take your questions now.
Hello?
Hi.
Hi, this is Max from UC Berkeley. Thanks for this. Is a very interesting talk. I sort of see two things going on with the Argus tool here. There's the interface with the bottom-up, sort of top-down tree exploration, which is very neat. But then there's also this, I mean, you have to, as you said, there's a lot of X's that could potentially lead to a valid proof, and you sort them. And of course, in the example that you gave, the sorting does a very good job, right? It puts the thing that you actually wanted in the very first thing. So I'm wondering if you could say a little bit more about, like, to what degree is this inertia heuristic the secret sauce in these other domains that you're sort of, wanting to look into? Do you think a version of inertia could work, or are you imagining? I guess, like, maybe even in your user study, did inertia always put the correct thing at the top, near the top? How much would that affect a user's, benefit from using your tool?
Yeah, so inertia is quite important in this case because, as you said, we have lots of information and users probably aren't going to read through 100 lines just to try and find the one that they may or may not know is the one they want. In our user study, inertia does quite well, and we have details in the paper of how it compares to, like, the Rust compiler heuristic as well as some other simpler heuristics we tried. For other domains, I don't know what the heuristic would be there. Someone would have to provide it, but I suspect that there is a inertia-like heuristic that we could use to try and help users out a little bit. Did I get all of your questions in there? Okay, thanks.
Hello, I'm Christine Riscala from the University of Melbourne, and yeah, thank you for your talk. I was curious about identifying bugs versus fixing bugs, and whether the same sort of information you think would be, like, most helpful, that would be most helpful in one case would be most helpful for the other, or if we were to help people even more with fixing bugs, what's your intuition about?
Yeah, so I can show you the information we do provide for fixing bugs right now. So if you see, we have, like, this is actually a different example, so bear with me for a second. There's a type that doesn't implement some trait, and so we can tell you the things that do implement that trait, which is very similar to what the compiler does. We can just do it for the more specific trait that you need. There are cases when this is kind of difficult. So one common pattern in Rust is the type state pattern, where depending on the type you have some methods available. And so we believe that, fixing errors in the type state pattern probably requires some notion of that state machine that you have, and that users would want access to that. But it's an area we haven't quite explored. Thanks.
Good. Time for one last question.
Martin Mars, Google DeepMind. Thanks for the great talk. I really enjoyed this. I'm curious about comparison to AI and LLMs. So you mentioned in the user study, for example, that people had access to a chatbot, but I was wondering, if you build an AI-based tool around this and you give it all the code and you give it the error, do you have a good sense for how that would compare against your approach?
I have no idea. So I can tell you in the user study, people used all sorts of LLMs, online ones, local ones, chat-based, Copilot, whatever. They all did terribly, so nobody actually ever fixed or localized an error with an LLM. I would suspect that in order for this to actually work, you'd have to train the LLM on, like, one specific library and your code and tell it exactly what you're trying to do. And sometimes these questions aren't, like, the developer might not know exactly what they're trying to do, so there's a little bit of fuzzy bits around the edge. But I suspect that an LLM-based approach would require a very specific LLM to one library.
Cool, thanks.
Yeah.
All right, let's thank Gavin for a great talk. Now, our next speaker is Marissa Kirasame, and Marissa's at Utah, and I just want to put a plug in for Marissa, who's nearing graduation, and so will be on the market soon. So go have a chat with Marissa after the talk if you're looking to hire someone. And Marissa's going to be speaking about spineless traversal for layout invalidation. Over to you, Marissa.
Hi. So let's open a web page. Let's say we're opening Google Chrome. No, Google. Then what happens is the browser has undergoes a long and complex pipeline to convert this HTML DOM tree to pixels on the screen. This pipeline includes JavaScript execution and garbage collection, CSS matching and styling, and layout and rendering to convert it from the tree to pixels. Now, what happens when the user clicks a button on the web page? Then the corresponding JavaScript will be executed, modifying the HTML tree. Now what we compute is now stale, and we have to recompute them again. One sec. Because the web browser want to keep a smooth user experience of 60 FPS, and because layout is only a tiny part of this pipeline, this means layout typically get a budget of 1 millisecond. On this tight budget, every cycles matter. So how does browser deal with this huge computational demand? Two tricks, incrementalization and amortization. In particular, this means that when the tree is changed, the browser don't immediately recompute the layout. Instead, the browser merely marks what is affected by the change with a dirty bit. Only later on, when this layout is requested, do the browser go find all dirty nodes and fix them in one go. So with this add of incrementalization and amortization, this incremental layout is 100x faster than from scratch layout. So this is a pretty critical optimizations. So let's see how this algorithm works in more detail. In here, let's say we have a single node that's dirty, the red node. Then this algorithm has to go find that red node and fix it. But by recomputing the node, note that this fixing itself also counts as changing the tree. So now its dependency is dirtied. And we have this cat and mice game again. Now let's say this time, when we are recomputing this node, it's the same. We doesn't change anything. Then everything is good. We don't have to dirty the dependency, and we can stop here. The stopping is important because with it, typically for each external dirty node, we only have to do like 3 to 5 recomputation to fix everything. So that's how the algorithm works. To sum up, it has 3 parts. It has to find all dirty nodes. It has to recompute them and dirtying all their dependency. Now this run in a loop until all dirty node is resolved. Now a lot of prior work has focused on the other 2 parts, recomputing node and dirtying them. For this talk, we want to focus on finding dirty node as fast as possible. Let's see what the state-of-the-art do. So this is the state-of-the-art algorithm trying to find this red node in the bottom. To find this node, the state-of-the-art algorithm traverses the tree top-down, touching all orange node. Now this orange node we call auxiliary node because we touch them only to find the red node, not to recompute them. As you can see, we are touching about 20 to 30 auxiliary nodes, and each of them is an L2 cache misses. This means we are paying 1,000 cycles just to find the red node. And the computation of the red node is typically not 100,000 cycles. So in here, we have a von Neumann bottleneck-like situation where we are spending more time finding out what to compute rather than computing So here's our solution. What if we just don't traverse the tree? Instead, we use a queue to store pointers to the node that is dirtied. Then we have a similar loop. For each element in the queue, we dequeued them, we computing them, and enqueuing their dependency, which is newly dirtied. We execute this loop until the queue is empty. Then no more things is dirtied, and we are done. So let's look at this example here. In here, we have a single dirty node. Now, this dirty node is in this queue. Now, processing that doesn't touch any other node. We just jump directly according to the pointer. Then, its dependency is also enqueued. Again, we jump directly to this node. Now, this time, maybe we are dirtying its two dependency. They are both enqueued. And then we are going to process them one by one. For this case, let's say processing it does not change the tree. Then we are done. Now the queue is empty, so this process ends here. Okay, we are talking about this queue. Does it matter what order do we insert element in the queue? And does it matter what element, like they're processed? For correctness reason, it turns out no. Any order is good as long as the queue eventually gets cleared. But yes, for performance reason. So let's look at this example here, where we have a tiny tree of 3 nodes. The left node is dirtied. Processing it will include its two dependency. Then let's say we are processing the top dependency first, and the right dependency later. Now, this right dependency may include the top dependency again. Then, what this means is the top node is included and processed twice. This is bad because we are doing extra work. So what can we do? We can try to make this queue clearing process the same order as if we are doing a from scratch layout. Now this must work because a from scratch layout only touch every node once. So to implement this from scratch layout, what we can do is we can tag each node with a timestamp. Then this timestamp is assigned when the node is finished computing initially. And this timestamp increases monotonically. Then we can index our queue with this timestamp. Let's see how it is implemented and its performance characteristic. In your implementation, in heap, we are using a main heap on a pack and a flat array. Because we typically have less than 100 nodes, this means the whole priority queue is in cache. Then the bottleneck comes from the invocation to the comparison function. Now, the queue is 100 nodes, so that translates to 8 comparisons per push or pop. And because each comparison is 5 cycles, the total time per push pop is 40 cycles, which is a single L2 cache misses. This means as long as the baseline state-of-the-art algorithm have a single auxiliary node for each dirty node, we are already on equal ground. In real life, the state-of-the-art algorithm has much more auxiliary nodes, so this means we are winning in real life. Okay, so what should this timestamp be? It turns out it can't be a usual 64-bit integer. Here's why. Let's say we have a tree of 3 nodes again. The left node have a timestamp of 4. The right node have a timestamp of 6. Then let's say we want to insert a node in the middle. What should its timestamp be? It has to be greater than 4 and smaller than 6, so that's only 5. Let's try to insert again, and this time we are out of gap. So we need something other than an integer timestamp. It turns out that our firm people have come up with this idea of order maintenance, which presents the idea of infinitely splittable time. It provides two API exactly what we need, comparison and insertion. It is critical that both of them are O1 with a small constant of typically dozens of cycles. Comparison is the critical operation because a single node is inserted once and compared many times. So let's see how we can optimize comparison. The implementation of comparison is as follows. It takes two pointers, A and B, and it computes 4 timestamps. The 4 timestamp. Finally, it lexicographically compares the 2 up timestamp, then the 2 down timestamp. As you can see, this code has 2 bottlenecks. One is that we are doing pointer access on here, and each of them is potential L2 cache misses. And other is we are having an unpredictable branch. This unpredictable branch will cause pipeline stall, which is about 20 to 30 cycles on a modern CPU. So to solve the first problem, what we do is we use a custom allocator, packing all timestamp tightly, packing all nodes tightly. Then, moreover, since the nodes are packed tightly, we can now use pointer compression. So each node is only half its original size. Now, per cache line, we are fitting 4x more objects. Then, to solve this unpredictable branch problem, we Sure, good. We eliminate this unpredictable branch. Instead, we are gonna use hand-write assembly to use conditional move. Now, this whole comparison is about 5 cycles. So to sum up, the problem of incremental web layout is they are gonna have too much auxiliary node and suffer the von Neumann bottleneck. We solve this problem by using a queue to store the dirty node, and this queue is indexed by all the maintenance timestamp. Now let's see how it works. We evaluate our algorithm, spineless traversal, over the baseline algorithm on 50 websites. These 50 websites are what you and me use, like Google, Twitter, GitHub, Lichess. We modify Ladybird, a web browser, so that every time it tries to lay out, it prints out the HTML DOM tree. Then we compute a diff of between these DOM trees, and we fit the diffs into our baseline algorithm and our algorithms. The result is plotted here. We have 2,200 points, and each frame is a data point in the scatter plot. The plot looks like this. Most point is below this x equal y black line. This means for most point, we are winning. Let's break down this plot down. Overall, it is a 1.8x geo-mean speed up. As you can see, this plot is made up of 2 kinds of points, one on the top right quadrant and one on the bottom left quadrant. On the top right, what happened is an initial load frame where the browser just finished network loading and is presenting a huge diff for the incremental algorithm to handle. In such case, we are paying the extra cost of creating all the maintenance node, so we are a bit slower. But in this case, the user is already waiting for the network load anyway. For the small frames, they are what we call a forced layout. This means that multiple small changes is done inside a single 16 millisecond time frame, and each of them must be laid out separately. So the small frames come in group, and they must be handled quickly. So all in all, this is a 1.8x geo-mean speedup on the more important part of this whole data set. We are talking about incremental web layout, but what we have done instead is I've built a general framework This framework works with different kind of place where we have dirty bits, or we can use incremental evaluation. For example, we have modified our approach to work for type checking in IDs and structural editors. See our upcoming paper in Uppsala. It also works for, like, let's say, parsing, compiler, just anything attribute grammar. So if you're interested, get in touch. Any questions?
Thanks a lot. It was really, really interesting. I really like this. So I just want to know about basically memory footprints of this, because I think you are using some additional memory to compensate the computations.
Yes. Absolutely. The extra memory footprint we use is this order maintenance object. This means for every node in a tree, we are using about 128 more bits of memory. This is not that much because each node in web layout typically is like 1,000 bytes of memory. So this is like a few percentage more overhead, but it may differ from different applications.
Okay, so you said that it may differ, but it is proportional to what factors? What factor basically?
It's not a factor, it's a constant of like 128 bits.
It's time for another question if we have one. I've got a question. Could you just say a little bit about the applicability or the difficulty of transferring this into other browsers? You evaluated in Ladybird. Now, I know that browsers are very, very complex things. Can you just say a little bit about that?
Yes. In fact, what we do is we build a custom DSL, a custom compiler, and then evaluate our algorithms on that custom DSL. So we didn't really evaluate it inside Ladybird. The problem with web browsers is that they are like, the layout part is like hundreds of thousands lines of code, and it's gonna be really difficult to swap in a replacement.
Great, thanks. Let's thank Maurice for a great talk. Our next speaker is Farnaz Barang from Uber, and she'll be talking to us about Dr. Fix, automatically fixing data races at industry scale. Thanks, Farnaz.
Thank you. Hi, everyone. This is Farnaz from Uber, and today I'm going to present our paper, Dr. Fix, automatically fixing data races at industry scale. So writing concurrent program is easy in Go. So you have a function call, you prefix it with Go, and it will run concurrently. So in this case, it would be an unstructured parallelism, meaning that the parent function does not wait for the child to finish. But let's say you write all of these concurrent programs, but when does the data race happen? So a data race occurs when two or more threads, or in the case of Go, we call them Go routines, concurrently access the shared memory, and at least one of those accesses is a write operation. So many of you might not know that Go is a language that is highly susceptible to concurrency bugs, including data races. So here is a real-world Go function, which comes from the Uber code base. And you don't really need to know the details of the code, but at the high level, it's a function that it fetches the balances from all the payment accounts in parallel. So there is a parallel loop here, and there is two racy access of the shared variable, which could cause a data race. Now, let's execute this program together. So let's imagine there is a user that has an Uber account with a balance of $100. And although they concurrently add two $100 values to their account, and they expect the updated balance to be $200, expect to be $300. The updated balance might end up being 200 because of the data race bug, which is going to make the user unhappy. So we have deployed a dynamic race detector that uses threat sanitizer for Go at Uber. And in the last few years, it has found more than 8,000 data races in the 100 million lines of code of the Go code base that we have. And our team has studied about 2,000 of these data races in a paper that was published in PLDI'25, which is about these different data race patterns. And so one thing we noticed over the years was that the number of races that has been detected was per day was more than the number of the races that the developers can fix. And on average, it took developers 11 days to fix each of these races. And this is mostly because application developers are not necessarily concurrency experts. Okay, so then that's when we started asking this question that can we automatically fix these data races? And so what are the challenges there? There's like a bunch of racy patterns out there. So means that the solution space is large. Log protection is not always the correct solution. And especially in the case of Go, it's more challenging because the Go supports both message passing and shared memory as a means of communication between the Go routines. And there has been some prior work. Most of them has been rule-based approaches that only covers a small space of the real-world problems. And with the advancement of the LLMs over the last few years, then we wanted to know if large language models were able to fix these data races. So let's say we have this threat sanitizer-based stack trace. We throw it at LLM. Would it be able to come up with the fix or not? And this is what we use as a baseline to compare our tool against. So we have this rich database of the past bugs and manual fixes that the developers have done before. And we wanted to leverage these and see if LLMs would be able to come up with more and better fixes using these patterns. So using these past boxes and the fixes that developers have done, we generated the bug embeddings and created the database of these bug embedding examples, and also used some smart search to find the good example, which is the closest matching example for the new bug that has been filed to generate more and better fixes. So basically, the two key ideas behind Dr. Fix is generating these bug embeddings and the smart search that we do. So in the next few slides, I'm going to talk about each of these ideas in more details. So let's first start with the bug embedding generator. So this is a step that we mostly do offline. And so given a curated list of the bug and fixes that we have, it extracts a pair of the RACI code and the fixes and generates the concurrency skeleton for the RACI code and uses that as a key in the vector database that we have, along with the pair of the buggy code and the fixed code as a value. But what is this concurrency skeleton that we use as the key in our vector database? So let me explain that to you with an example. So here again is a real-world Go program from the Uber code base that involved in a data race. So we have a Go routine, one Go routine here and another Go routine here, and there is this air variable that is shared between the Go routines and has a RACI access. So in Go, if a variable in the Go routine is used from the outer space, it uses the, it doesn't have the value of the object, but points to the reference of that variable, not the value of it, and therefore it causes the data race. So now let's see, look at the concurrency skeleton on the right side. So you can see here that we have the air variable that is renamed to the RACI variable, and all of the concurrency structures in the Go, such as the Go and wait, are renamed as is. But the rest of the statements are dropped, and all of the other types, functions, and names that are not related to the concurrency are renamed as just generic names. And so to achieve that, it uses a specialized form of program slicing. And if you're more interested in the details of that, you can check out our paper. Okay, so the other thing is that we use the smart search. So given these trait sanitizer-based stack trace, we want to find the candidate code locations where the data race might exist. But what are these candidate code locations? So based on our empirical findings, most of these data races have a fix that exists either in the leaf function of the stack trace, the root function, or the least common ancestor function between the parent and child go routines in the stack trace. And these are the ones that we consider as the candidate code locations. So now that we have these candidate code locations and the vector database of the past examples, let's see how the GenAI-based fix generator uses the retrieval augmented generation to generate the fix patches. So given these candidate code locations, it generates the concurrency skeleton for them and compares them with all of those concurrency skeleton that we already generated in our offline step for all those past bug fixes to find the best matching example for that particular new bug. And this is provided along with those candidate code location to the GenAI model to generate these fix patches. And then each of them is getting validated. So we compiled it, run all of the tests with the concurrency mode, and then if there's any failure, this is fed back to the LLM, and this process is gonna continue until it will come up with a validated fix, or it just times out. But let's take a look at what are these different attempts that we do with the LLM. So we have this feedback loop that, so first of all, we look into the different granularity of the code as a coding context. So basically, it operates on the function level, file level. So we have all of these build test error messages that we collect and feed it back to the LLM. And also in terms of RAG, we use not use RAG at all, using the RAG without the concurrency skeleton, and also using the RAG with the concurrency skeleton that we have generated. So with all that, if the fix generator is able to generate the validated fix, this validated fix is provided to the developers for review, and if they approve the fix, then this will be landed into our code base. Okay, now I'm going to briefly talk about the impact of the Dr. Fix at Uber. So we looked into applying the Dr. Fix to the Go code base of the Uber, which contains of 100+ million lines of code. The LLM model we used was GPT-4o, and the size of the examples database that we used was 272 of the past bug fixes that we had. Then we applied that in 204 reproducible Go data races, for which the tool was able to generate fixes for 55% of them. And of those 55%, 88% of them were approved by the developers. And with that, these manual fixing times, that was 11 days per race, came down to 3 days per race. And this excludes the investigation time that the bugs are like waiting in the queue. And then we wanted to know what are these different categories that these bug fixes belong to. So we went and manually categorized them. So these are some high-level categories. So the largest category was captured by reference in Go routine that accounts for 41% of the fixes. And the examples that I showed earlier in the talk belong to this category, captured by the references. And then we had other categories for missing or incorrect synchronization, parallel test suits, capturing of the loop variable, and concurrent map or slice access. So I'm going to show now 2 examples so you guys get a better idea how these other categories look like. So this is one example that for the missing or incorrect synchronization, So on your left side, you see the code before fix. And so you see there's a for loop, there is a go routine, and then there is this sync wait group that just uses like an add function on that. So what is sync wait group? So it's a synchronization mechanism in Go to wait for all the Go routines to finish before proceeding. And it mostly uses the atomic counters to achieve that. So in this case, what is expected that this sync wait group add we define outside the Go routine. But this is one of the classic mistakes that the developers make, and they define that inside the Go routine, which could cause the data race. And you can see on the right side the suggested fix to move that outside the Go routine. So another category, concurrent map access. So here you see a definition of a regular map in Go. And although this map has a per shard mutex-based locking mechanism, but still it could cause a data race because we have this run shard program that is run concurrently. So it iterates through the different items in the map and delete them if needed. And since this is running concurrently, so while one of the Go routines is going through that, deleting, it's possible that another Go routine does the same thing, and that could cause the data race. And in this case, there's another usage of the map as well that you can see that the values of the entries in the map get updated. Now, what is the suggested fix here is to use the synchronized map instead of the regular map in Go. And so you can see here that different usage of that map is also updated accordingly to use the just different APIs that belong to the sync map library. So next question that comes to mind is, what are the other categories of races that Dr. Fries was not able to fix? And so we manually looked into some of these past bugs that developers have been able to fix manually, but the tool was not. And then one of the top categories was fixes that belong to more than one file change, required more than one file change, or changing or reducing parallelism, changing the business logic. So there were some cases where the fix was in the external library, or some large code refactorings that the developers have done. So as you can see, for some of these categories, like changing the parallelism or changing the business logic, they might not be the easiest for the automated tool because they heavily rely on the intent of the developers, which might not be easy to extract automatically. So we also performed an ablation study to understand the contribution that each of these components that we added to the technique helped with the effectiveness of the Dr. Fix. So first of all, we wanted to know, compare the not using RAG, using a RAG but without our concurrency skeleton, and also RAG with the concurrency skeleton that we generate. So not using RAG at all, we were able to generate fixes for 47% of the data races. Then once we used the RAG, but without our concurrency skeleton, the number went up 3%. And with the concurrency skeleton, the number went up to 66%. So we also wanted to evaluate the impact of our feedback loop using different scopes and error messages. And as you can see here, using the function only, file only, as just a scope or coding context that is provided LLM, or the file plus the pass failure messages is not as effective as providing the combination of all of them. So to wrap up my talk, so today I talked about the concurrency bugs, in particular data races, which are pervasive and they are hard to fix. So although Go makes it easier to write these concurrency programs, at the same time it makes it easy to create these concurrency bugs as well. And there has been some approaches in the literature, but most of these are rule-based approaches that have limited reachability. And that's why we proposed Dr. Fix, which is a Gen AI plus program analysis-based technique to catalyze these data fixes. And with that, we were able to reduce the fixing time from 11 days to 3 days. And it has been deployed at Uber, and it has fixed more than 200 bugs in a span of roughly about a year. And the key ideas behind Dr. Fix is uses the bug embedding plus the smart search. And so we believe that a general idea of using these code skeletons helps make LLMs more effective for different software engineering tasks. Yeah, that's all I had, and I'd be happy to take questions.
Thank you for the interesting talk. I might have missed it, but how exactly do you match the newly found bugs with the keys in the database? Like, I don't think the skeletons will exactly match.
Right, so we generate the embedding vectors, and then we do the distance vector of those embedding vectors to find the closest match.
I see, thank you.
If you could state your name and affiliation before asking the question.
Kimi Yo, Privaska Latier. So do you have any metrics on whether or not these kinds of cure-all tools like Dr. Fix, whether they lower the quality of the code base because it could make your developers more complacent, given that I don't have to write concurrent correct code anymore, and I'm just going to let this super tool find the bug for me and fix it for me automatically.
So even before we have deployed the Dr. Fix, we have these 8,000 data races that it was found in the developer's written code, right? So this was kind of the solution to help the developers fix more bugs instead of having their time relying on just manually fixing those. We provide automated solution with them. And this is in general improving the developer productivity. Let's say you help developers having IDEs or other automated tools. So this is another tool in their toolbox that they can leverage to improve their productivity.
Another question? I think we had one at the back there. No? I'll take one at the front.
Hi, I'm Marissa from University of Utah. Thank you for the talk. Can you break down the 3 days race fixing time? What goes in it?
Oh, okay. So it starts when the developers start working on the tool, start working on fixing the bug from the moment they pick up that. Then, so they have sometimes they just write the code and stuff, and then they raise the diffs for the review, and someone reviews, then approved, and then it's landed in the code base. So from the time they start to the time it's landed in the code base.
We have time for one more question.
I'm Param from Microsoft Research. I was wondering if you have experimented with asking the developers about the bug, taking their input, maybe a couple of lines of data that they know about the code. How has that helped? Are you looking into that?
So you mean asking their opinions about the tool?
Yeah, maybe raising it as an issue, asking them for comments on that issue, or what the PR that you generated, whatever the comments were about that, and incorporating into another fix.
Right. So I think actually we did also user feedback that we reported in the paper that I didn't talk here about, but I think we had I think 3.4 out of 5 user satisfaction on the use of the tool, and then I showed that 88% of them were approved by the developers. So we had 12% that was not, and so in terms of the feedback that we got for the reasons that developers rejected the fixes. It was basically sometimes they wanted like better readability for the fixes that was generated. Also, they wanted to use a different approach to fix that. So, and then also sometimes they thought it's not like the correct fix. So.
All right, let's thank Farnaz for a great talk. All right, the final talk in our session is going to be delivered by Bo Wang, who's at the National University of Singapore. And he's going to talk to us about program skeletons for automated program translation. Thank you, Bo.
Okay, so hi everyone, I'm Bo from National University of Singapore. Now I'm going to present our work on code translation. So the title is Program Skeletons for Automated Program Translation. This is a joint work with Tianyu, Ruishi, Wumang, and Pratik. Okay, so first, why do we want to translate programs across different languages? There are several possible motivations. And first, when we want to migrate legacy code to modern languages. So this figure shows that the popularity of programming languages, they're changing in the last 20 years. And sometimes we migrate the code base because the distribution of software is shifting. And the second, from the software security perspective, we want to move code written in memory unsafe languages to safer alternatives. And third, sometimes there exist some useful libraries written in one language, such as Python, but developers in another language, such as JavaScript, they want to have some similar functionalities. And automated code translation can help there as well. Okay, so despite its potential usefulness, we don't really have much success in this problem. There are at least two requirements for the task. So first is correctness. So means that we want the translated program to have external, the equivalent external input-output behaviors. And the second is scalability, which means that we want the translation mechanism to be able to deal with realistic long software. And so people have been working on this for a while. And 25 years ago, there was an interesting technical report on the experiences of real-world code migration. At that time, a comment that language conversions are as easy as turning sausage into a pig. Basically says that automated language conversion is much more difficult than many people anticipate. Okay, so why is it difficult? So let's look at a very small example with 2 lines of Python. It creates a dictionary object and prints a result. So assuming we want to translate this piece of code to JavaScript. So traditionally, the traditional way of it is building a compiler. So we indeed have some Python to JavaScript compiler. If we give it to the compiler, it will give us some code like this. So we can see that first, it looks more verbose than the source. And second, if you look closer at the code, we'll realize that the translation is actually emulating a lot of stuff in Python. So including data types, APIs, and all these emulated constructs are injected by the compiler. So essentially, the translation is trying to lower the Python code to a subset of JavaScript with emulated language constructs. So such translation is far from ideal when we want to migrate software. And this phenomenon is not specific to Python and JavaScript. So I'd like to quote the same report that basically investigated COBOL and to Java translation, but here we said you could call such translation JavaScript compliant Python program, but not necessarily JavaScript programs. Okay, so more specifically, such translation has 2 main issues. First, it is very hard to preserve every detail of the source. So you end up with ugly code when trying to be correct. And the second, it may defeat the purpose of the translation. If you want to migrate from legacy dependencies, it preserves all the legacy dependencies. If you want more performant code, and you might be disappointing if the translated code is a lot of emulation. So let's revisit the requirements of automated program translation. The correctness and scalability are probably the most explicit requirements, but there are also implicit requirements such as we want the code to be readable, maintainable, using native language constructs, etc. Or in one word, we want the code to be idiomatic. So this shouldn't be overlooked since, as earlier work also mentioned, imaginary advantages often motivate the conversion process. So as we all know, 20 years later, we have code LLMs. And if we give such a piece of code to these models, it will produce translations that are much more idiomatic. However, as basically evaluated in various previous work, these models work fine for small pieces of code, but struggle to produce correct translation when dealing with slightly longer programs. So in this paper, our main contribution includes the following. First, we propose a technique named program skeletons that allows idiomatic translation of long programs. And second, to basically go with the skeleton, we propose a common abstraction of program semantics that is suitable for the purpose of translating across language. And third, we implement a prototype named Scale, which can handle realistic Python programs up to 2,000 lines of code. Mostly automatically, yeah. So let's first look at the high-level idea of program skeleton. So it is actually quite simple. Given a source program, we decompose it into a skeleton and associated code fragments. The skeleton is basically an incomplete program with holes. So then the skeleton and the fragment will be converted to the target language and get composed into a complete translation. So to demonstrate how it actually works, let's first start looking at an example Python program. So assuming this is a Python program we want to translate, we don't need to understand the statement level details, but only look at a high-level structure of it. So the entry point of the program is a code in the global scope. And here the entry point has some whole program tests. And besides the global scope, we have two top-level functions named compute and multi. So within the function compute, there's a nesting closure definition with function name update. So note that these code fragments will actually interact with each other if we execute the program. So if we roughly look at the execution behavior, the execution will start from the entry point, which is a whole program test, which calls the function compute. And within function compute, it will try to call another function multi and passing the closure update. And then within the function multi, it will try to loop over an array and call the closure. So overall, this function has three functions, including one escaping closures and 4 lexical scopes in total. OK, so if we want to translate this using program skeleton, we will first offer using a syntactic decomposition of it. So basically decompose it into a skeleton K and the code fragments G0 to G3. The executable code inside each lexical scope is one fragment. So now we have 5 pieces. We can start to construct the translation. So we can perform a direct rule-based conversion of the skeleton, which will deterministically produce a mirroring skeleton in the target language. And then for each code fragment, we can use LLMs to produce candidate translations and then try to fill in the holes of the skeleton. So since we cannot really trust the LLMs in the generated code, we need to somehow check if those code fragments are correct. So this can be tricky to tell whether the translated fragment is correct because idiomatic translations, first, they look very different from the source. And then second, these fragments may interact with other code fragments in various ways. So the question is, what kind of program behaviors should be considered equivalent in our translation task? So there are several ways to think about the problem. We need to find a common way to model the semantics of the source and the target. So first, we may consider modeling each piece as a pure function. So including the skeleton itself as well as the fragments, so if we model each of them as a pure function, and also if we can somehow replicate the same set of pure functions in the target language, and if we can check their input-output behaviors, and if they match up, we say each fragment is equivalent and the whole translation is equivalent. So such a style of semantic modeling is probably suitable if the code is pure, but not a suitable choice if we are dealing with procedural code with different kinds of side effects. So to naturally capture side effects, an alternative way to model the problem, to model the semantics, is to consider the program as a state transition system. So in such a model, control flow transfers between code fragments, and this transfer will be associated with state transitions to a shared memory state, so represented by a RAM value in the figure. So however, the problem of such a modeling is that such memory states, they will capture low-level details that are language-specific and may not actually transfer over to a different language. So for example, consider the for loop in the program we showed earlier. If we look closer at the memory state, at the time of control flow transfer to a different function, we'll see that there are stateful objects and variables such as iterator zip or variable x that doesn't necessarily make sense for the other language. So what kind of semantic abstraction is suitable for a translation task? Ideally, we want our common semantic model to achieve 3 goals. First, capture side effects. And second, abstract away low-level language-specific details. And third, it should allow some decomposition, which means that if we can determine the equivalence of individual fragments, then we should know for sure that when we combine, the combined translation is definitely correct. So we can see that pure function not really suitable and or straightforward for modeling code fragments with side effects and shared state transitions. They capture too much low-level details. So what is a better way to model the problem? So we propose to model the execution of code fragments within the skeleton as a set of communicating processes. So conceptually, we can think the program skeleton K as the process 0 that communicate with fragment processes, for example, P1 and P2 in the figure. So each process has private memory states that is external to the process. So the only way for processes to exchange information is by communicating through messages sent and received between the processes. So in this abstract model, we expect a correct translation to replicate similar semantics, basically the same set of process and the same messages in and out of these processes. And we consider it is sufficient for the translated fragment to be considered correct as long as the messages are equivalent to the source. Note that it does not require the internal states of these processes to be equivalent across the languages. Okay, so far we have explained the high-level idea of program skeleton. To build a runnable prototype to test it out, we implement a tool named Scale that translates Python to JavaScript. So we made several design choices for practicality considerations. First, we focus on dynamic analysis and correctness under test. So the benefit is that the analysis of APIs, loops, recursions, and dynamic types are made much easier. The downside is that it can be incorrect if the tests are insufficient. We use a rule-based compilation of the skeleton, and the benefit is that ideally it can work regardless of the program size. The downside is that we do assuming that the translation has a common high-level structure with the source. And we use the LLMs for synthesis of code fragments, and it gives us readable and idiomatic code. The downside is that there's no guarantee that LLM will give us the correct result every time. So when it fails, the mechanism needs to somehow deal with it. Okay, so more specifically, Scale works in 2 stages. The first stage focuses on skeleton generation. So Scale takes an input program, normalize it, and then generate a syntactic skeleton. So with the generated skeleton and the decomposed fragments, we perform dynamic analysis to collect traces that are basically expected messages in and out of the processes in our semantic model. So these pieces of information basically give us the syntactic and semantic constraints of our translation task. And the second stage is to reconstruct a program in the target language satisfying those constraints. So we have 2 goals in the second stage, basically the translation stage. So first, we want the constructed target program to pass the test by construction in the ideal case. And secondly, if error inevitably happen in the translated program, they should be isolated to an individual process. Like we should be able to know precisely which code fragment is the root cause of error. And otherwise, if the error propagates, we will not be able to know where to fix. So our solution for the second stage, the translation stage, is a procedure named execution order translation loop. So it works by performing the translation incrementally, following the natural execution order of the program. So in the beginning, we only have the target skeleton without any field fragments. So as we execute it on the whole program test, the translation procedure will gradually fill in the translated fragments and check step by step. So at each step, we only check for the corresponding to one random interaction with a single process of some code fragment. So for example, if the check pass, then we simply, it means that that fragment at that execution step produces expected outcome, and we continue with the next execution step. Okay, but sometimes the check didn't pass, and which means that an error might exist in the corresponding code fragment. And in that case, the translation procedure will refine the translation query as well as performing iterative repair until it passes a step. So ideally, with a powerful enough LLM, after such translation loop terminates, we are guaranteed to have a whole translation that passes a test. In reality, is that when LLMs cannot resolve an error after retry a limit of 3 times, the procedure will pause until human users fix the highlighted code fragment so that the procedure can continue. So to evaluate scale, we collect a benchmark of 9 Python programs with lengths up to around 2,000 lines of code. 3 of them are modules from the Python standard library, 2 of them from popular repository on algorithm implementation, and another 4 popular Python libraries from GitHub, each with around 700 to 1,000 lines of 1,000 stars. So this figure shows a result. We run in scale with both GPT-4 and GPT 3.5. The green bar shows the percentage of code fragments that are automatically handled by scale. And the orange bar shows the fragment of code fragments that needs to be fixed by human to allow the translation loop to continue. So overall, scale with GPT-4 can automatically handle 95% of all the code fragments, and scale with GPT 3.5 can handle 85%. So it is worth noting that after the translation loop terminates, all output program pass whole program tests. So we also show how scale compare with baselines in terms of how much user fix is needed. So here we choose our first baseline as a GPT-4 with a simple strategy that basically translates function by function. And we choose our second baseline as transcript, which is a compiler-based tool that translates Python to JavaScript. If we sum up the numbers of user fix, scale with GPT-4 requires 23 fixes, or 5% of all the fragments. And GPT 3.5 requires more fixes, but is still lesser than the baseline with GPT-4. So besides the numbers, it also worth noting that it is more difficult to debug and fix the baseline translation since we don't know where exactly the bug is. Because sometimes if we just run the program, we report runtime error, it may not necessarily be the bug. But Scale does not have the problem because it has the semantic checks and it will report to the exact fragment needs to be fixed. We can also see that the compiler-based transcript is not able to run on 5 of the 9 programs. It is because that these programs use language features and APIs not supported by the compiler. Okay, so to summarize, program skeletons offer a promising decomposition of the code translation problem. And there are definitely more work need to be done to eventually turn sausages into pigs. For example, we need to handle more APIs, different kinds of external effects, file network, and etc. We also need to support more language features such as multi-inheritance. And it's also interesting how this can be extended to other pairs of languages. Yeah, that's all. Thanks for listening.
Thank you.
Hi, thank you for the talk. I'm Jose, University of Edinburgh. I want to ask you, if I want to use your technique in arbitrary languages A and B, what should A and B be like? Like how similar or how different they can be so your technique would work on them?
Oh, right. Yeah, okay. So the question is about if we want to use it in other languages, how similar should the language? Yeah. So this technique is probably works the best for untyped languages. It is designed for untyped languages, but it can be also extended to other languages. I mean, static type languages, or like if it's procedural code. But for static type languages, I mean, we probably need more work. So what the semantic analysis in this paper is not sufficient, for example, to deal with C2 Rust. Yeah. So that would probably require more advancement. Yeah.
Hi, Michael Ficara, F5. My question is about performance, not performance of the translation process, but performance of the output program. it wasn't mentioned explicitly as success criteria that the programs would have similar performance, but I'm assuming that it should be, and assuming that it is it possible that that goal would conflict with the desire to create idiomatic programs? I'm thinking as an example, two different string types in different languages would have different performance characteristics because one might store it as like UTF-8 encoded, one might store it as like a sequence of code points, and then the same string operation would have different performance. So is that possibly in conflict with the making it idiomatic?
Yeah, okay. So what we didn't mention in this talk is that it actually has a type mapping. So for this semantic check to work, there need to be a mapping of objects and types. And for that, I think it can be customized, it can be changed if you prefer a specific data type. And in that case, the translation is forced to use that type. So it should be like be customized for your job. Yeah.
Yeah. Thanks for the great talk. It's a really interesting project. And I was wondering, is there a clear boundary or a clear guideline to make the skeleton, to implement the skeleton technique? So the syntactic structure of the source language and the target language could be different. For example, if you want to translate a for loop, there could be many ways to implement the for loop in the target language. So, but if I force the target language to use a specific loop structure, it's going to lose some idiomatic structure in some ways.
Yeah. So actually, we try to present. I guess it's kind of one general way to decompose the program, and so the way we are dealing with it is that we simply decompose by the lexical scope, and all the executable code within lexical scope is one fragment. But the same idea can be applied, for example, if you want a for loop to stay similar, you just decompose the inner part of the for loop. And you can still model them as fragment processes. Just there are slightly more analysis need to be done to figure out what is the input and output of those processes. Yeah.
Right. We have time for just one last question.
Hi, Leonard from University of Montreal. So thanks for the talk. I had a question around semantics. So sometimes semantics around languages, even a simple for loop can be like completely different. And I know here your goal is to like keep it idiomatic, but I was wondering if you could share maybe some insights around how you can deal with these cases where, for example, in Python you cannot put anything in a body of a lambda. Yeah.
Yeah. Okay. Yeah. So I think the mechanism is designed specifically for that. So you can do arbitrary things in Python. You can put a for loop in a list comprehension, but the analysis only observes the communicating messages of that conceptual process or what will be in and out of the fragment. So it will observe, for example, several function calls out of it, and it really doesn't care how you initiate these function calls. So you might initiate using a comprehension or a for loop or just a bunch of repeating statements. So it will be considered equivalent.
Great. And with that, we close out a great session. Thank you, Bo. And let's thank all of our speakers.
All right, folks. We'll get started just in a minute. So find a seat. Sweet. Welcome to the architecture session. I'm Rachat from MIT and Jane Street. I'll be chairing the session. We have an absolutely fantastic set of talks for you in this session. And starting us off is Sardeep, working on sort of this very interesting problem of trying to program data flow architectures and sort of thinking about how you can take classic ideas in programming languages and imbue them with like some amount of superpowers to bring these kinds of architectures to sort of some amount of sanity. Please take it away, Sardeep.
Yep, thanks. Hello, everybody. So Ripple is some work that I did with my advisors, Nathan Beckman and Brandon Lucia, and an awesome undergraduate at CMU, Yufei Shi. Let's get started. So spatial data flow architectures, or SDAs, are a general purpose accelerator platform that runs programs spatially as a data flow graph across an array of processing elements. SDAs are fast and efficient, but only for some simple regular code. More complex programs can get too big, so they might not fit on the architecture, and they might also get very poor utilization and performance. Our insight is that many of these applications, like this graph traversal on the left, have what we call coarse-grained data flow behavior, where program regions communicate data to other regions asynchronously, maybe with a work queue or a task pipeline. SDAs should be a great fit here because their hardware pretty much implements exactly these semantics. So what's the problem? Too many SDAs use low-level languages like C, which force the user to write data flow behavior down as a bunch of low-level memory and control flow operations that compile inefficiently. So that graph traversal gets a data flow graph from C that looks like this, which is it's complicated, bloated, and might run pretty slowly. So the problem here is what we call an abstraction inversion. We have a model of data flow behavior in the application and in the hardware, but we lose that information because we lack the software primitives to lower cleanly to SDAs. So our solution here is simple. We want to expose asynchronous data flow semantics of the hardware directly in the language. And so that way the user and the compiler have the primitives to lower efficiently to an SDA. And so Ripple implements this solution. It's a language and architecture that corrects this abstraction inversion. So specifically, Ripple has explicit language support for asynchronous execution, work queues, task pipelines, and synchronizations to program SDAs. And in the architecture, Ripple exposes hardware token queues in its ISA, so that the compiler can achieve a nearly one-to-one mapping of Ripple code to existing SDA hardware. So that same graph traversal compiled from Ripple is going to be much faster and much smaller than the one compiled from C. And the trend is clear on a variety of workloads. So Ripple is on average 3 times faster and nearly halves the program size compared to a state-of-the-art SDA that compiles from C. So for the rest of this talk, we'll look at how SDAs work, the abstraction inversion problem, how Ripple solves it, and some results. So let's highlight a couple of key basics about SDAs. So spatial data flow architectures compile some code to a data flow graph of dependent instructions. And that DFG is mapped to a spatial fabric of PEs, each of which runs like a handful of instructions or even sometimes a single instruction for the duration of a program. Instructions talk to each other directly through a network on chip. And so if we zoom in slightly, we'll see hardware queues at each PE. And these queues automatically manage input data that's coming in for each instruction. And so an important takeaway here is that instructions are communicating their inputs and outputs using hardware queues. This is ubiquitous in all SDAs, and it's going to be a point that we'll come back to later. All right, so if you want to run a program, SDAs use what we call the data flow firing rule. And so there's no instruction stream or program counter. Instead, inputs arrive and queue asynchronously at a PE. Instructions then fire whenever all their input data or tokens, which are the gold circles, are available. And independent instructions can fire in parallel. And so tokens sent between instructions are automatically received and drained by hardware queues. The last piece we'll look at is how SDAs get high performance. And it's because of instruction-level parallelism and pipelining. So to give an example, we got a simple for loop here in some C-like code. And then we'll compile it to a DFG, which has this kind of concise and simple pipeline structure with an iterator at the top and a multiply and a store. We'll kick off this loop and map what happens with each instruction using a pipeline diagram that will organize into time steps. And so if we kick off the iterator, it produces I equals 0. And then as tokens flow downstream, we'll notice that more and more instructions are ready to fire. And the loop iterator also keeps firing again and again, kicking off more loop iterations. And so this is pipelining. And the SDA is doing it at the loop level. And so this kind of filled out pipeline diagram is exactly what we want to see for all of our applications. And so good pipeline parallelism means that we'll get good IPC, utilization, performance, and that's what we're going to try to achieve with Ripple. All in all, we saw that when done right, SDAs can really exploit this asynchronous pipeline parallelism for good performance. So the abstraction inversion problem in SDAs cuts right into that, squandering a lot of that good pipeline parallelism. So let's take a look at how that happens. So to demonstrate the problem, we'll complicate our example a little bit. We'll use breadth first search, or BFS, as the example. So for an input graph, we'll try to calculate the BFS tree corresponding to the search, represented by this parents array. We'll have some outstanding vertices to visit along the way, which we'll track at the bottom. And just to be clear, the graph on the left here is the input to the application. It's not a DFG. OK, so BFS is essentially the following steps. We're going to grab a vertex, like 1, and then we'll filter for unvisited neighbors for those vertices, like the bright red ones. We'll set the parents of those neighbors, and then we'll need to traverse vertices again, which we'll track using a work queue. And so this process continues until we're done with the traversal. So BFS here is essentially a set of pipeline stages that are dynamically communicating with each other. This here is coarse-grained data flow behavior. And so SDAs should be great at BFS because we should be able to pipeline as much work as possible through each stage by continuously dequeuing and enqueuing work through BFS's work queue. And more importantly, SDAs should be really good at handling BFS because the work queue could be handled by a hardware queue. So unfortunately, though, many SDAs, like the prior work on the right, compile their programs from C or C-like code, which lacks abstraction for data flow semantics. And so in C, if we write that asynchronous communication with a work queue down, it's going to be a full software queue using an array in memory and push and pop methods. Operating on that queue is just as rudimentary. We're going to need something like an irregular while loop because we can't express an automated pipeline with concurrent push and pop. And so what we've done here is the C code has inverted the abstraction of queue-based asynchronous communication. And that a data flow architecture should be able to easily implement this with existing hardware. There's also a lot of consequences in compilation. So the abstraction inversion forces the compiler to implement a lot of low-level memory and control flow instructions of the software queue, instead of reasoning about the high-level coarse-grained data flow behavior in BFS. And so this is detrimental for a number of reasons, mainly memory ordering. Memory ordering is something that a data flow compiler implements when they have a lot of potentially aliasing and racing memory operations, and the compiler serializes them by adding a lot of control flow to preserve sequential memory semantics. And so this happens in BFS. So for instance, in this for loop, so remember that the SDA is going to try to pipeline iterations of this loop. But we have a racing read modify write to parents that exists across loop iterations. And so load in a later iteration might read a stale value before an earlier iteration finishes updates. And so a compiler is going to look at this, and it's going to serialize by adding control flow instructions, which we represent with this red arc here. Also, since the SDA is going to try to pipeline the outer loop as well, push and pop are also ordered to ensure that we don't pop from an empty queue. And so here the impact is a lot worse, actually, on program size and performance, because longer ordering arcs need even more control flow, because we need to route signals inside and outside of control structures in the code. And so the result is this monster-looking DFG that we saw at the beginning. We've caused one of the two major problems in SDAs. The program is way too big. And so in particular, the bold bordered red nodes, especially on the right side of the graph, are inserted for ordering only on the software queue, which already itself takes a lot of instructions to implement. And so a bloated DFG like this might not even fit on the fabric. All right. Compiling from C also causes another major problem of low utilization and performance. And so I'll try to demonstrate this with BFS running on this input graph. And we're going to try to mark what happens using a pipeline diagram with different parts of the C implementation. This is what we want to have happen. We want to have this perfect pipelining where we pop a vertex, we're going to iterate over its neighbors, and we're going to update parents. And then on the side of the work queue, we want the same kind of thing. As soon as we enqueue a vertex, we want to dequeue it and extend this pipelining from push to pop. But in reality, that's not what we get. So updates to parents are serialized in that for loop that you can see in the third and fourth row of the diagram. And so we lose some pipelining there. But ordering push and pop is even worse. So memory ordering here forces each outer loop iteration to finish before the next one starts, and we can pop again. So we serialize the entire loop nest. And so all the gaps in the diagram are indications of low ILP and utilization. And so that means that if we compile from C, we're going to eliminate all the nice pipelining that we have. All right, let's see what Ripple does about the problem. So Ripple is a language in ISA that corrects the abstraction inversion. Ripple structures programs as asynchronous regions that communicate via queues. And so these queues can be lowered to hardware queues in the architecture. So for BFS, it allows communication between each step, including and especially the work queue, to lower directly to a hardware queue. Ripple enables us to cut straight through the software queue implementation in C, its API, and the irregular while loop. And instead, we can write down traversal logic using Ripple's asynchronous iterators, or asyncs. So in Ripple, users distribute code into asyncs that run asynchronously from each other and run in parallel. And so here, BFS has two asyncs, one for initialization and one for the bulk of the work. So let's dive into some of the key properties of an async and Ripple's push primitive. So asyncs have a name, an input list, and a body of code. And an async defines an implicit queue of inputs that it iterates over, executing the body for each input set. And so inputs to that queue arrive asynchronously. And each iteration launched is something that we call a task. And so each inputs drain automatically, meaning that we're going to launch some tasks, and those tasks are going to pipeline. Push is our primitive to define a data flow dependence between asyncs. And so that allows for direct asynchronous communication of data between them. And so in our case, queue pushes to itself. And so if you put all of these components together, we can drain the vertices into tasks of the async queue, pipeline them, concurrently add work back to the queue using push. And so a lot of these semantics should seem familiar. So if we look back into SDA land, we can see that an async captures the semantics of asynchrony, queuing, and pipelining semantics that data flow execution and hardware queues have. And push defines a dependence that's effectively a DFG edge. All right, so let's see how the Ripple ISA implements async and push. So Ripple builds on a recent data flow ISA called Riptide. We borrow its arithmetic control flow and memory instructions, but we also expose hardware queues and token arbitration in its ISA by adding queue and arbiter instructions. So queue here defines a hardware queue, and an arbiter performs round-robin selection of inputs to feed a queue. And so if we revisit BFS, we can see how this works. So remember that BFS has these two asyncs, and async inputs here for a queue are going to map directly to a queue instruction. Pushes map the DFG arcs into an arbiter, which selects an input to pass along. And so the entirety of BFS's work queue can just be captured using two instructions. And so now you might be wondering why we need a queue instruction at all if Ripple maps data flow to existing hardware queues. Most of the time we don't. The compiler can actually fold the queue instruction into hardware queues of downstream operations. But in certain cases we can't, when we can't bound the size of the queue. So BFS actually exhibits this property. So BFS has the thing where we push work from the queue back to itself. And if the queue were mapped onto a hardware queue, it could deadlock if that queue fills up. And so we could implement the work queue with loads and stores, but that has all the problems that C had. What we do instead is we add spilling to the queue instruction. So a single queue instruction can dynamically spill to memory as needed to avoid deadlock. And so Ripple's compiler here is going to identify queues to spill. And Ripple's microarchitecture supports spilling with minor changes. But I'll leave some of those details for the paper. But supporting cycles here really expands the scope of programs that Ripple can implement. And so this is a key advantage over prior data flow languages, which I'll talk about a little bit later. So that covers async and push. But Ripple provides even more primitives to enable more pipelining. So for instance, if you remember, Ripple and the C program had this race on updates to parents here, which requires ordering that still hurts pipelining. To eliminate these ordering edges, Ripple provides atomics. And so atomics acquire a set of input addresses, like parent sub NB. It executes the body, and it releases those addresses implicitly. Atomics dynamically order racing accesses to parent sub NB, which are rare in this case. And we've designed the architecture for Ripple so that they pipeline. And so that enables a lot of performance. And you can also read about that in the paper. So by solving the abstraction inversion problem, Ripple generates a fast and concise program for BFS. All right, let's try and put this all together. So remember this from the C implementation, which is how C was performing on BFS. Ripple improves over that by eliminating all the stalls in the C version of the program to perfectly pipeline using tasks and atomics. All right, so now we've seen how Ripple works. I wanted to talk a little bit about why you should use it to program SDAs over other options. So there's been a lot of asynchronous programming languages. And these languages are great, but they don't exactly solve the abstraction inversion problem for SDAs. So some of those primitives in those languages might mismatch by offering too much or too little by way of semantics. And so channels in Go can be manipulated, for instance, instantiated and used arbitrarily, but Ripple queues only support push with automatic task spawning semantics that matches like the underlying SDA hardware. And so there's also been only a few data flow languages, and all of those have limitations as well. And I'll skip over those in the interest of time. But Ripple here gives you only a few primitives, so you can express exactly the data flow semantics supported by SDA hardware. And so there's a detailed discussion of that in the paper, which I'll leave for now. And you can read a lot more about it, the architecture and whatnot in the paper as well. All right, let's look at some results. So we evaluated a variety of workloads using real and synthetic inputs, and we compared to two systems, Riptide, a state-of-the-art SDA that compiles from C, and a sequential von Neumann processor, and we simulated these results. So the main takeaway here is that Ripple is fast. So we plotted speedup of Riptide and Ripple over the sequential von Neumann processor. And so these bars here show a geomean speedup of our workloads. And so what you'll see is Riptide is already fast compared to the von Neumann processor, but Ripple achieves way more performance, amounting to a 3x speedup over Riptide. The rest of the bars here show performance for each workload. Each workload was evaluated on 2 inputs. And if we look at these graph workloads, for instance, we get a lot of performance by eliminating software queues and enabling workless style parallelism. We get similarly good performance for linear algebra workloads, where we use Ripple to build coarse-grained pipeline stages, which eliminates a lot of the ordering. So Ripple gets big speedups across the board on all of these applications. Our other takeaway is that Ripple programs are small. So here we measure program size as the number of static instructions. And so for instance, for BFS, Ripple, which is abbreviated as RP, more than halves the program size compared to Riptide, which is abbreviated RT. And to understand how Ripple does this, we can split our instructions into control flow versus non-control flow. And Ripple eliminates a lot of the control flow that BFS has in the Riptide and the von Neumann version by getting rid of software queuing and using atomics. And so we see this trend across the board for all of our workloads. On average, Ripple is going to shrink our programs by 1.9 times. All right, so today we looked at Ripple, a language in an ISA that solves the SDA abstraction inversion problem. And it achieves significant performance and program size improvements over the state of the art. Thank you for listening. So I'm open to questions.
Folks, please feel free to raise your hand or stand up, and the volunteers will get you the mics. Question back there.
Yeah, thank you for the great talk. I'm Andy from Georgia Tech. I just had a small question, I guess, about like how you collected your numbers. So sure. Because like I guess Ripple comes with its own ISA and like dedicated architecture. So I guess how did you run everything? I'm assuming some sort of simulation, and like how did you like ensure like a fair comparison between like the CPU, Riptide, and Ripple?
Yeah. So I'll talk about like the way that we simulated is we run the data flow graph. And we don't do a full system simulation with like energy numbers and hardware and that kind of thing. So this is a higher level microarchitectural simulation. But we had a prior simulator that was built for Riptide, and that was close to the RTL that we implemented. And Ripple borrows from that ISA. It adds a few instructions like for atomics and queuing. And so we've implemented that on top of that simulator. And so we run the data flow graph and get numbers in that way. The von Neumann processor we're emulating LLVMIR. And the reason we do that is because those instructions are the closest to the ISA. So if we did something low level like RISC-V, we have stuff like moves and that kind of thing, which data flow architectures don't have. So that was kind of the fair comparison there.
I'd like to understand better the atomic construct that you have, and to what extent it's compile time versus runtime. Do you have to worry about detecting deadlocks or anything like that?
Yeah, so that's a good question. So we talk about this at length in the paper. I'll answer all the points there. So when you write down an atomic, what the compiler is doing statically is it's looking at the input addresses, and it's implementing memory ordering for the atomics with respect to other atomics and other racing accesses around it. That's one part. The other part is dynamically, we have a hardware directory. And so when you do a set of acquires, we have acquire and release instructions in the architecture. And those are working together with the directory to like dynamically acquire addresses and reserve and release addresses if you need to. There is a possibility of deadlock with atomics. And so we use the same idea of spilling. So basically, if you have two sets of atomics, and they're communicating like a live out from one atomic to another, you could pile up a bunch of tokens and deadlock. And so spilling solves that problem in the same way that we do for tasks.
Any last questions? Sweet. Let's thank the speaker one more time. For our next talk, we have Thomas. Thomas is an assistant professor at EPFL and has been working at the intersection of hardware design languages, computer architecture, and programming languages. And if you know anything about hardware, you know it's like massively, massively concurrent. And this talk has a very enticing title about how you can sort of get a handle on all of that concurrency and do all of your cool verification tasks. Thomas, please take it away.
Thank you. Let me put the timer. Okay, thanks for the introduction, Ratchet. So I will present some work that I did while I was still a grad student a few years ago, and it's a work with my co-authors, Elvis Liu, and my advisors, Adam Shipala and Arvind. So as Ratchet said, I've been doing architecture and verification, hardware verification for a while, and sometimes I have the syndrome of grass is greener on the other side. And when I look at software verification, one of the things that is very standard that I like very much is the modularity that is at the core of many approach. One of the key things is like you can have a class that can be verified against a specification that assigns a precondition and post-conditions to each method. Then the methods are proven each in isolation. And then a client of the code can verify their own functionality without ever needing to look at the implementation. On the hardware side, the story is a bit different. The abstraction that we work with is an abstraction of the actual circuit. It's called the register transfer level abstractions, where you have a state, typically a bunch of registers that are updated every so-called clock cycle with a Boolean function. And the good thing about that is that it's such a low-level representation that you don't need to get married to a new programming language to do verification. All the verification flow works at a very low level. And it works with Boolean equivalence, and it allows you to do bounded model checking. The bad thing is that there is no notion of function calls, object, and method at that granularity, and so there is no good notion of modularity, and verification doesn't scale very high. Very useful, but doesn't scale for full functional correctness. So our goal for a few years has been to try to verify functional correctness of interesting computer architecture designs in an ITP. And to do that, the first thing that we wanted to do was to recover software-like modularity in hardware design languages. And so to tell you that, the first thing we are going to do is to not write hardware languages. We are going to write in a slightly higher level of abstraction called BlueSpec. So I need to tell you a tiny bit about BlueSpec before I tell you about what we did to BlueSpec to make it more amenable to verification. So in the BlueSpec system Verilog methodology, as an architect, you often draw these kind of diagrams where you want to design a pipeline, and you have some function F, some function G, and you would like to write a hardware that does that. And in BlueSpec, the way you do that is you don't write a state update function on registers. You just describe that machines as a bunch of objects, which are the submodules, the 3 queues, in, mid, out. And you write the methods that your new module has. There's an enqueue method here, where you can push stuff in the box, and a dequeue and a result method here. And the methods are basically things that are changing the state of the module, changing the hardware state, or observing the state. And there are rules that are, once you have pushed something to the machine, it goes on its own mind, and you can think of it in automaton term
as epsilon transitions. They keep going in the background non-deterministically, so it might pull from the in queue, push into the mid queue, pull from the mid queue, pull out. Submodules are recursively themselves of that form, method rules plus submodules, and you bottom out at modules which are just registers, which have just read and write methods, and BRAMs and a few other primitives. So the BlueSpec system Verilog methodology is you describe your hardware design in that lingua, describing submodules, rules, and methods, and then you use a compiler to derive the state update functions. And a few years ago, we had a PLDI paper to study the proof of correctness of such a compilation scheme, but we had not looked at, and there's been prior work looking at verifying not things here, but verifying things there on the left-hand side. And that's what the rest of this talk is going to be about. So it already looks like I have given you a software abstractions. Because they are objects like submodules and you have methods, so it looks like we have software abstraction. Well, there's a little plot twist here. The base modules that we have, a register which has a write and a read primitives. If I have a register that holds 42 and I write one of those rules that tries to write 1 to the module and then displays a value, actually it doesn't display 1, it displays the old value in the registers. And that's coming from the fact that BlueSpec being a hardware language, at the end of the day, it's just wires connecting to submodules, and the read always happens before the write in a clock cycle for registers. So the semicolon you can think of it as parallel composition instead of sequential composition. So when you describe a rule, you are simultaneously doing all the actions that you are calling onto the submodules. So here, read after before write happens before write. This very simple issue creates a problem when you try to characterize a module in isolation. Let's look at this module. And this module has 2 methods, write A and write B, 2 methods to update, and 2 methods to read A and read B. And intuitively, there are just 2 registers hidden inside. If I were to write a client that try to, oops, sorry, there's a typo, it's not set A, it's write A, and it's not get B, it's read B. If I read B, put it in A, and read A, put it in B, then if I try to characterize what this thing is doing, you can think about it in your head, then it's not going to be a state update that is explainable in terms of sequence of calls to those methods. If I had 0, 1 in A and B, after I do that thing, I'm going to get 1, 0. I would have swapped the 2 values, and I will never be able to explain that behavior in terms of a sequential behavior. It's not a sequential behavior. So this is a fairly annoying problem. And this led previous work, Adam and Arvin at work in 2015, Cami, that so the problems that we always try to do is proving a refinement. You have a complex implementation with an interface, you have a simple specification of the same interface, and you want to say that all the behaviors on the left-hand side are behaviors of the right-hand side. But because of this concurrency issue, all the behaviors, including not just sequence of method calls, but sequence of sets of method calls. You have to consider that every time I could try to simultaneously call enqueue and dequeue, enqueue and result, result and dequeue, and so you have a power set of things to consider. So if you wanted to prove an equivalence between modules, you needed to basically consider an exponential number of cases, and that in all those cases, your complex implementation was indeed producing a behavior that was in your simple spec. So you can't characterize, you could not characterize a module 1 method at a time. So this was a little limiting because it made refinement harder to use. And it was not really necessary, so we did this very childish step of saying, do we really need to be able to call multiple action methods simultaneously? So normally in the previous work, every method was considered the same kind of methods. Methods that change the state and methods that read the state were all smashed into one family of methods. And we did 2 childish steps. We started by saying, let's separate methods that purely update the state from methods that are observing the state, called value methods. And then let's simply forbid calls that calls 2 action methods of the same module in the same rule. When you do that, you're morally restricting the language to multiple readers, single writers, where concurrency and management is much simpler to handle, and BlueSpec can basically do that, and then you can explain every behavior in terms of a sequence of behaviors. So we did that. I will tell you in a minute why that doesn't hurt expressivity. But what it gives us to give this restriction is that then we can characterize a module in BlueSpec as a very simple transition systems and with a very simple notion of equivalence between transition systems. So the notion of transition system will be denoted by the type of the state will be the product of the submodule states. The rules are simply going to be relations on states. The methods are going to be of 2 kinds, relations and action method and relation and value methods. which are state cross arguments cross new state and state cross arguments cross new value return. And that's basically just a mass description of any BlueSpec module. Very convenient because once we have that, so we can model partial transitions and non-functional relations for non-determinism. But more importantly, we are on the highway in terms of theory. We can reuse very well-known theory of weak simulations to be able to study how one system is implementing another system. And I'm going to go quick on the details there. You can read the paper for more. But the key thing is that it gives us a nice substitution principle that is exactly what we were looking for. That is, if you can prove that a module implementation refines a module specification in the sense of weak simulation, then any usage of that module will refine any usage of the specification. And that's exactly the idea of saying for verification purpose, we never manipulate the implementation. We always manipulate replacing the implementation by the specification to study the bigger module. So we typically use case is like, let's say that in your hardware design, you have a circular buffer implemented with NQ pointer, DQ pointers rotating around. You don't want to do verification on that. You have a lot of symmetry of equivalence. It's very annoying. The first thing you do is you prove that this refines a list-based, non-synthesizable specification. And then when you do your verification of your module using that list, you are using only the list-based version. And you have a theorem proven in Rock to do that. So now let's use all that theory. Actually, before we use all that theory, let's assess a little bit the restrictions on can we still write useful BlueSpec design with that restrictions. We did a little static analysis to the BlueSpec compiler to basically assess is it the case that existing code was violating those assumptions or not. And we fed it about, I think, 300,000 lines of code. And we found a few violations. I don't want to get too much into detail. I can tell you later if you're interested. By the way, it's a good way to find places where students 15 years ago wrote hack, hack, hack in their code. So now let's go to actually using this nice software-like refinement view of the world. So our use case is going to be a little processor. So we would like to study sort of a pipeline processor. And the theorem we would like to get is to say, well, if we were to plug this processor to like a terminal, which is talking to the processor, to the machine through an MMIO line, exchanging bytes on an MMIO line, then we would like to get the theorem that any interactions between the keyboard and the screen in MMIO to the pipeline processor are traces that could have happened in the simple specification processor. Where on the left-hand side, the processor is going to be slightly more sophisticated, that on the right-hand side, it just executes instructions one by one. And in this case, instruction and data memory are basically part of the system, but they are out of the processor. And the whole goal will be able to prove the processor independently of the memory. So the processor, the family that we studied is fairly simple and also complicated in one sense. So it's fairly simple because it's just a 4-stage pipeline. But it doesn't mean that it has only 4 instructions in flight. Actually, it has arbitrarily many instructions in flight because the size of the queues are arbitrarily sized. And it was very important to us to do that because we were especially interested in looking at verification in the context where you have speculative loads, where you have multiple outstanding data load or instruction load. Because a lot of complex things we're going to see are happening because of that. So the strawman would be to say, well, I need to prove that thing. So that's easy. I'm going to use a refinement theorem to just prove that thing. I'm going to prove that the implementation processor is a refinement of the specification processor, and then I will have won because I've used my refinement theorem to lift it up. And that would be sort of like, the natural modular verification strategy, except it doesn't work. Why it doesn't work? Because the theorem is not true. Why is the theorem not true? Because the pipeline processor has actually many, many, many more behaviors than the simple specification that emits the load and the stores one by one. Think of it like this. In the implementation, my processor might back-to-back send 2 instruction requests back-to-back before it even gets a response. It speculates 2 instruction requests. On the right-hand side, this will never happen because you only emit the next request once you have got the response for the instruction and once you have finished the full execution. So it's not that the theorem is hard to prove, it's that the theorem is false. This behavior does not exist in the processor specification. So we were very excited because we realized that this simple problem, we didn't even have a spec for it. We don't have a valid spec just for a processor. We have a valid spec for the full system, which happened to be made of a processor and a memory, but we don't have a spec of just a processor. And we are not talking about multi-core weak memory model, this kind of business here, right? We are really talking about single core, but doing the study of the processor in isolation of its memory. So to solve this problem, basically we are taking an opinionated stand, right? We are saying we need to tell you, architects, what are all the possible things that all the possible optimizations that your processor should ever be able to do? How many load what kind of load you should be able to issue, the reordering between load and stores. That's what such a specification should say. So it sounded like a hard thing to come up with. How do we write a spec that can cover any possible processor implementation in the future, or at least all specific processor implementation, which was just pipelined? And the idea is very simple. The idea is to say we are going to stitch together this sequential 4-cycle machine. We're going to stitch it with 2 non-deterministic load machine. Instead of the processor sending its request directly to memory, it's going to send it to what we call a load buffer. And that load buffer is not just buffering the load, it's also emitting random loads to random address at any point in time, non-deterministically. So the way we think of this is basically we say the spec of a processor is not just the spec of a simple ISA machine that goes one by one. It's that plus just you randomly add a bunch of loads anywhere, any address. Because architecturally speaking, loads don't matter. You know, data speculation techniques can be very wild. You would never know where they will send a load, when they will send a load. So conservatively, just say you could send a load anytime, and that's going to be your new spec. And we will just, there's a little bit more things on store, but I won't elaborate on that much more. So why is it the case that the generalization is valid? Well, architecturally, it's kind of obvious, right? You know, there's this saying that loads don't matter, only store matters. But is that intuition formalizable? And yes, it is formalizable, because we need to be careful. We can't just change our specification. I just changed the rule of the game. I told you the old spec didn't work, let's just replace it with a new spec. But if my new spec was I could also send random stores, then I would have just said nonsense. So the theorem that you get is the following. So on the first hand, you're going to prove that your processor refined its generalized specification, which is basically simple processor plus random loads. You do that, then you apply the refinement theorem. You get that theorem below. And then you need to prove another theorem, which is the correctness of the generalized specification. That is, from the perspective of the outside world, from the MMIO request perspective, these extra loads you sent did not disturb the system behavior, the system level behaviors. And that's a second proof that you need to do, and it's actually not very hard because loads actually don't matter. So we verified a few more designs. Elvis wrote a network switch, a programmable network switch with a nice specification, which is deeper than the processor. And then we proven a crossbar as well, and a processor, a family of processors. All of that, you can find more details in the paper. So what I wanted to tell you today was 2 simple things. First, we can characterize hardware modules one method at a time in the software world. But when you get that, you're not done, because you are facing the standard problem that actually writing modular specification is hard. And you need to find a way to generalize the different components you want and to say all the acceptable behaviors that those subcomponents should have for your full system behaviors to be true. And in the case of processor and memory, we are quite excited because we are getting into a way to decouple the memory from the processor. It's actually sort of bringing memory model questions even in the single core core setup. There is more, I think in my dissertation, maybe not in the paper, on that. But it's very interesting. It gives us a way to start reasoning about weak memory model in a more operational way. And thank you.
Please raise your hand if you have questions, and the volunteers will bring the mic to you. Just to get us started, so there's this very interesting insight that sort of the simple sequential specification of a processor is not actually the right one, and you have to add some amount of non-determinism to sort of make it general enough to actually prove properties against it. I have 2 related questions. One is that, are there other places you think you would need to add non-determinism to express the kinds of microarchitectural optimizations people are sort of thinking about? And 2, oftentimes people want to test the specifications, which are higher level, and sort of think about how to compose them in a broader system. Now that you have so much non-determinism and so many traces that sort of might look foreign, what do you do with that?
Yes, so both are interesting questions. So the first one, about other places where you need non-determinism. Yes, so actually the first example that we had was an example where you have so we used to always study GCD machines because those are very simple machines but are very interesting. So little hardware blocks that can compute GCD between 2 numbers. And you would like the spec of that things to be just something that just take an input, produce a GCD, and produce the output. And if you have an implementation that does a lot of reordering and that does a lot of things, then you do need a step of generalization to make it work. And it's actually quite easy to do, to write this generalization. So I think there might be something about that in the paper or in my dissertation of a simpler case of generalization. Which is exactly this idea of sometimes you might need to add a queue somewhere, sometimes you need to add a little out-of-order completion buffer somewhere. Logical, it's not a physical thing in your spec, but that works. Then in the processor case, I think, yes, the answer, actually the things that I outlined, we turn out that you can sort of draw a bridge between whatever you write here and whatever is your weak memory model. So if you're abiding by a weak memory model, one given weak memory model, then there is basically one kind of wrappers that you need to write around it. And so if you have a different weak memory model, you will have a different kind of wrapper. So you don't generalize the same way depending on your weak memory model. And that's a difficult question that we have not finished answering yet. Outside of memory, I don't know. So we have only looked really seriously at the boundary between processor and memory. I've looked a little bit at the boundaries, at other boundaries, but they are more inside the processor, and there we didn't need generalizations. So it's kind of, it really depends. And then your second question, I forgot what it was about. It was testing. Yes, testing. Problem was non-determinism. Yes, non-deterministic testing. Yes, it's hard, and we don't know how to do it.
Nathan Beckman, CMU. Do I understand correctly that you constrain that the stores have to come out of the processor to the memory in the order, the same exact order of the sequential?
So that's, I explicitly say that I didn't say anything about it, right?
Yeah.
So you're asking me to tell more about it. So in the implementation of the processor in the code that is in the artifact, yes. Then we slightly tweaked it because obviously some person was not happy with that. And we basically glued together a store buffer and a load buffer. And in that situation, then you can have reordering in your store buffer. So you don't emit the store directly. You let it go through the store load buffer. So if you remember, they did I2 paper a few years ago at ISCA, and we are reusing some of those ideas there.
Thanks.
Let's thank the speaker one more time. Awesome. For our final talk, going back to the theme of sort of using programming languages, ideas to program weird new machines, this work's really interesting where we're sort of, the authors are trying to figure out how to use the capabilities that new kinds of hardware is exposing to sort of prove strong security properties about their systems. This is going to be a remote talk. Well, it might take a second for this to go through. All right, I guess take it away.
Hello. Hopefully I'm visible and audible, and someone will yell at me if I'm not. So yeah, this is Morello Cerise, proof of a strong encapsulation property for the Morello capability architecture. So first thing first, I'm talking about capabilities. In particular, I'm talking about Cherry capabilities. Cherry is a family of architectures with hardware support for capabilities. The Cherry capability is basically just a sophisticated sort of fat pointer. So in addition to an address, it's got bounds and permissions that describe what memory accesses it's allowed to authorize. And that's super important because on Cherry architectures, all memory accesses have to be authorized by an inbound capability with appropriate permissions. And sort of the first order use of this is you've got some program in a memory unsafe language like C or C++ or what have you. You compile it to a Cherry architecture, compiling all the pointers into capabilities, and you get almost for free a ton of fine-grained memory safety without having to make significant source code changes. And this is really wonderful because C and C++ programs are all riddled with memory safety violations. So we can fix large classes of them with minimal source code changes without having to rewrite everything in Rust. And that's Cherry in general. Morello in particular is a Cherry architecture based on 64-bit ARM. And among the many wonderful things about Morello, it really exists in real silicon. It's research hardware, so it's not generally available, but it means if you are working on Morello things, you can test them on high-performance hardware. So I said that sort of the basic use of Cherry was getting fine-grained memory in memory unsafe languages, fine-grained memory safety in memory unsafe languages. But what we want to look at here is, can we do a little bit more? Can we do some actual like program encapsulation powered by Cherry capabilities? And so what do I mean by encapsulation in this context? You have if you have a program or a block of code with some internal data, can we protect that data such that even if the program is running in the same address space with arbitrary, potentially adversarial code, that data can only be modified in ways that is allowed for by the encapsulated code? And the answer is yes, we can do this, but we do need one more feature of Cherry capabilities I haven't mentioned so far, which is sealed capabilities. On Cherry, any capability can be sealed, and a sealed capability can't be used to authorize memory accesses until it's unsealed. There's several different kinds of sealed capability. They all support slightly different unsealing mechanisms. For anyone familiar with Cherry, I'm not going to go into a ton of detail, but in particular in this case, we're using indirect sentry capabilities, which, like most kinds of sealed capability, are only unsealed by branching to a specific piece of code. So it's a bit abstract. Let me give a concrete example of the kind of thing that we'd like to be able to do. Imagine we have some little C function here. It's got an internal piece of data, this accumulator, and the interface is very simple. You pass it a number, it increments the accumulator by that much. For some reason or another, we take the mod 64 of the accumulator, and then we return it. And so the only values this code will ever write are values 0 to 64. The only values this code will ever write to the accumulator. If we just write this in C and we link it with code we don't trust, we can't rely on those being the only values in the accumulator, because the unknown code that we're linked against could guess the location of the accumulator and write whatever value they want there. And so what we want to know is, can we, on Cherry, protect this internal data using sealed capabilities? And the assembly you want to do this ends up looking something like this. All that's really going on here is the accumulator capability, the pointer to the accumulator is sealed, and it only gets unsealed when we call f. Somewhat remarkably, the code here is sort of very similar to the code that you'd write without having to worry about capabilities. The only major differences are, you'll see the register C29 is a sort of special capability register. That's where the pointer or the capability for the accumulator is being stored. And we have this extra instruction, the clear tag, that invalidates that capability before we return, which is how we avoid leaking an unsealed capability for the accumulator back to our caller. Right. And then the other bit of magic happens when you call this function. We have to use this particular variant of the branch and link instruction that will unseal the accumulator capability at the same time as branching into F, so that the accumulator becomes accessible to F without being accessible to F's caller. And if we do all this and we get it all right, we do know that even if it's called by arbitrary adversarial code, this invariant, the accumulator is between 0 and 64, always holds. It's a little bit finicky, and it would get worse with larger programs. So the thing we might want to know is, can we prove that these kind of invariants hold when Morello is used to encapsulate code? This is a surprisingly subtle property, because it requires reasoning about both the concrete known code of the accumulator and whole architecture safety properties about how much unknown code can do. And these are both independently tricky things to do on production scale architectures, and they only get worse when you try and do both at the same time. We do start from the good place of knowing a way to combine these two different types of proof in at least some contexts from the Cerise project. So Cerise proves results very similar to this. It comes in two parts. You've got a separation logic, which is a pretty standard machine code separation logic, which you use to prove invariance of your sort of known encapsulated code. And Cerise also provides logical relation that characterizes exactly when it's safe to call potentially adversarial code without risking it violating your invariance. And the fundamental theorem of that logical relation is a proof that it is safe to call on to branch into unknown code when you've satisfied the conditions of the logical relation. This is wonderful. The big downside is Cerise works with a radically simplified capability architecture. So if we want to prove things about Morello, we need to port it to a much larger architecture. And that difference in scale is a real problem. To give an impression of how significant it is, the Cerise architecture semantics sort of in prose fits on one page of A4. Their proofs are all about a ROC implementation of that semantics, which is about 700 lines. Compare that to Morello. The Morello manual is several thousand pages long. It includes large chunks of the ARM architecture reference manual. We do have a mechanization of Morello, which is really nice. It's written in ASL, and we can compile it to ROC via the SAIL ISA specification language. But you get more than 100,000 lines of ROC. And this scale is just completely fatal to an attempt to naively recreate Cerise from Morello, because the Cerise proof strategy for unknown code is to case split over all the possible instructions that unknown code might execute, and then do manual separation logic reasoning about each of them to prove safety. And that kind of approach is just completely intractable at this scale. So if we can't do this sort of per instruction manual reasoning, can we say anything at all formally about the behavior of unknown code on Morello? And previous work provides a partial answer to this. So the T-cherry properties are a set of whole architecture properties for unknown code that are specified and proven in Isabelle. There's a bunch of them. Just one, for an example, says, for example, that whenever an instruction writes a capability to a register, it must be the case that that capability is derivable from capabilities previously read by the instruction. If you take all the T-cherry properties together, you get quite a nice domain separation property, which basically says if you have multiple non-interacting code domains that are separated by not having capabilities to one another's memory, they run as though isolated. But that doesn't solve our problem because for two reasons. The property we want to reason about, A, involves interacting domains, right? This function, this accumulator function that I showed, is called by and returns to adversarial code. That's a kind of interaction. And also because the property isn't just a property that we want to prove is not just a property of unknown code, right? It also depends on the correctness of the encapsulated code itself. So we need to be able to reason about both together. We do have tooling for reasoning about concrete programs on large architecture specifications in the form of the Alaris tooling, which is a set of tools for automatically sort of simplifying architecture specifications when you're reasoning about a completely concrete program. So Alaris works by using Euler symbolic execution to take the large architecture specification and for a concrete instruction you want to execute, simplify it down to a set of register and memory access events. That's right, sorry. And Alaris also provides you with like an iris-based program logic for reasoning about the programs using that simplified specification. So this Alaris is great for reasoning about the known code of the encapsulated known code itself. But Alaris is almost useless in the presence of unknown code, because a critical assumption of Alaris is that we're able to do the simplification of the specification by knowing what instructions are going to be executed. So if we have Alaris that can handle known code but not unknown code, and T-cherry that can handle unknown code but not known code, obviously the solution is to combine them. We do this by extending Alaris with a notion of unknown instructions, which, whereas in Alaris most instructions have their behavior specified by a trace of memory and register access events produced by a symbolic evaluator, unknown instructions get a trace chosen non-deterministically at runtime, and the only property we know that it satisfies, the only thing we know about that trace is that it satisfies the T-cherry properties. To do this, we have to translate the T-cherry properties from Isabelle into ROC, and we do this by hand, and it's an assumption that we've done it correctly. We've not reproven them in ROC. Then we can just use Alaris exactly as is to verify our encapsulated code and whatever invariants we depend on for it. And we use a Cerise-like logical relation to prove unknown instructions safe. And we prove the fundamental theorem of that logical relation just on the basis of the fact, just from the fact that the unknown instructions satisfy the teacher properties, not based on any concrete behavior. So I want to give a quick impression of what the logical relation looks like. So it comes in two parts. We have this notion V that describes the set of capabilities that are safe. This is only the branch for V for unsealed capabilities. V itself is a bit too large to show in its entirety. Because this is saying that an unsealed capability is safe, we must take ownership of all the memory that the capability can be used to access. So we have that here. That ownership is inside an invariant because we need to handle the case of multiple capabilities that overlap. And then we have these read-cond and write-cond side conditions that basically just say that any values that are read or written from using this capability must recursively satisfy V. And then the other half of the logical relation is this notion E, which describes capabilities that are safe to execute. By capability being safe to execute, I mean the machine executes safely if we install the capability in the program counter. So the bulk of what's going on here is that if we have E of some capability and we have that all the values in general purpose registers are safe in the sense that they satisfy V, we get this WP, this weakest precondition, which says the machine executes safely without violating any invariants. The major subtlety here is you'll notice that these C29 and C64 registers are being treated specially, which is because they play a special role in invocations. But we also have this sort of more specific version of E that just universally quantifies over them for the cases where you're not doing an invocation. And with these two definitions in hand, the fundamental theorem of the logical relation is straightforward to state. It just says that for all capabilities, if they're safe in the sense that they satisfy V, then they're safe to execute in the sense that they satisfy E. The tricky part of proving this, as it turns out, is that unlike if we were doing sort of concrete reasoning over actual instructions, when reasoning about unknown code, all we know is that we get a trace of memory and register accesses that satisfies the T-cherry properties. So the only way we can possibly prove that safe is by induction over the structure of the trace. That turns out to be quite tricky because you need to sort of give your induction hypothesis, you need to describe what it means for the machine to be in a safe state with partially executed instructions. So you need to give a sort of characterization of what it means for the machine to be safe when a prefix, the trace of an unknown instruction, has executed. And that took us a while to figure out the details of. There's been something of a whistle-stop tour of how Morello-Cerise is structured and what it does. There's plenty more in the paper. So the full definition of V, including for sealed capabilities, which I didn't get into here. Our proof is based on the T-cherry properties, but we also had to extend them because they didn't give us quite strong enough properties in the cases of invocations. And so we had to figure out how to strengthen them and prove those strengthened versions in Isabelle. We give the full prefix safety property that I just described for proving the fundamental theorem. And we show how you can sort of, all of this taken together can be used to verify the accumulator example that I showed at the beginning of the talk and prove that this invariant on the accumulator is never violated. In conclusion, we've given a characterization of a basic encapsulation scheme for Morello. And we've proven the fundamental theorem of a logical relation that can be reused to prove that encapsulation scheme works with almost arbitrary encapsulated code. And as a consequence of doing this, it's worth pointing out that this demonstrates that it is in fact possible to prove strong properties of production scale architectures, even when that depends on combining reasoning about known and unknown code. Although admittedly, this process is still quite painful. And there's plenty of future work in sort of alleviating some of that pain so that these results can be further generalized. So the obvious work there is improving our automation. We definitely need better handling of sort of the complex instructions that you get on Morello in Alaris, because capability encoding and decoding generates very complicated traces. And it would be nice to have a better story about the integration between the Rock and Isabelle versions of the T-cherry properties. Sorry, that's it, and be happy to answer any questions.
Let's thank the speaker. Please raise your hand if you have questions, and volunteers have mics. So I'll start off with maybe a basic question, but do you have to worry about different kinds of code reentrancy problems when you're trying to do these kinds of sort of formal reasoning, or do you get to assume that the Cherry model sort of isolates you from all of that because you have these capabilities that are sort of managed securely?
So it depends on the kind of properties you want to prove. This is only a spatial safety property. And if you want to prove sort of temporal safety properties that talk about ownership of things on the stack, or things that you're sort of passing between compartments and depending on getting nice, well-bracketed control flow for correct evolution, you need a more sophisticated proof. The Cerise project there are more advanced versions of Cerise that do start to do this. We have not attempted that for Morello yet. There's a few reasons for that. One is just it's a lot of additional complexity, and we'd have to do both complexities at the same time. Although my impression is it's additive complexity, probably not multiplicative complexity, so I suspect it could be done. There's also lots of questions about how you do this kind of temporal safety efficiently. Lots of the schemes that people come up with involve clearing lots of the stack at every sort of domain transition, and there are ways around that, but they're not all well supported on actual Cherry.
Really interesting work. So can you say a little more about what the trace properties are that the ones that you took from Isabelle and axiomatized in Rock that you used to verify the fundamental theorem? Can you sort of say what those invariants are? I'm struggling a little to understand what what those trace invariants actually look like, and then how you build a proof over them.
Sure. So collectively, there's quite a lot of them. I can't run them all down. I couldn't run them all down off the top of my head, even if I had time. But so I gave the one, for example, if you write a register, there's one for writing a capability to a register, which says if the trace contains a write to a register and it's got a capability, and the value being written as a capability, it must be the case that there is one or more reads of capabilities, either memory or register reads, that come before it. And that the capabilities that are read before have some sort of derivability relationship to the one that's written. You get a similar thing for writing capabilities to memory. You can only write capabilities to memory that are derivable. All memory accesses have a condition that say you must have read a capability that has permission to authorize this access beforehand. Those are kind of the simple ones. It gets much more complicated when you deal with invocations. I can show them to you, but trying to sort of describe them out loud is taxing. And then the question of how you do a proof about them is you need to determine, once some prefix of the trace is executed, you have to write down a separation logic property that gives you enough ownership to carry out any subsequent actions that are going to be permitted. So in the simplest case, that you just have to keep track of all of the capabilities that have been read and know that you have enough memory ownership to perform any memory access that they would authorize. Because when you do a memory access, you must have, the properties tell you must have read a capability that authorizes it. So if we have memory ownership for all the memory regions that we've read capabilities for, we can use that to justify any memory access. That is, although I have not made it sound like it, that's the simplest of the things you have to prove at these trace intermediate points. There's a bunch of more complicated properties you have to prove to justify all the invocations. And the full property is in the paper.
Sweet. I know we have one more question, but let's thank the speaker first, and for people interested, can stick around. Free to go, but if there are other questions, please feel free to ask them.